You are invisible to most of the universe. Right now, at this exact moment, there are 2 trillion galaxies scattered across 93 billion light-years of space, and you will never see 90% of them. Not because you lack a telescope, not because they're hidden behind dust or gas or the glare of nearer stars, but because they are simply too far, too faint, too impossibly distant for any instrument humanity has ever built to detect. They exist. They are out there. Entire cities of a billion stars, worlds, black holes, collisions, births, deaths, all of it happening in a darkness so complete that no photon from those galaxies will ever reach Earth. And yet we know they're there. We've counted them. Astronomers have done the math, traced the structure of the cosmos, and arrived at a number that should make you stop and reconsider what you think you know about the night sky. 2 trillion galaxies, 10 times more than we believed just a decade ago, each one a vast island universe governed by forces we're only beginning to understand. Supermassive black holes 40 billion times the mass of our Sun. Ghost galaxies made almost entirely of invisible matter. Ancient structures that formed just 300 million years after the Big Bang, when the universe was still learning how to make light. And in 6 billion years, the galaxy you're standing in right now will collide with its nearest neighbor in a slow, violent dance that will reshape both beyond recognition. This is not a story about distant objects that don't concern you. This is the story of where you are, what you're made of, and what happens when you realize that every galaxy is a time capsule, and the light reaching your eyes tonight left its source long before your species existed. To look up is to look back, and the universe is still writing. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We need to talk about something uncomfortable. The universe you think you know, the one with its neat census of 100 billion galaxies scattered across the cosmic void like grains of sand on a beach, that universe doesn't exist. It never did. In 2016, a team led by Christopher Consellis at the University of Nottingham took decades of data from the Hubble Space Telescope, the Spitzer Space Telescope, Chandra Herschel, and XMM Newton, fed it through a mathematical model designed to account for what we couldn't see, and came back with a number that made the entire field stop mid-sentence. 2 trillion galaxies, not 100 billion, not 200 billion. 2 trillion with a T, as in 10 times more than the textbooks said. As in 90% of the galaxies in the observable universe have been sitting in the dark this entire time, while we drew our confident maps and wrote our confident papers about a cosmos we had barely begun to glimpse. Consellis himself said it plainly, "This is very surprising." Which, in the language of astronomers who spend their careers being careful with words, translates roughly to, "We have no idea what we've been looking at." The observable universe, the bubble of space we can theoretically detect from Earth, spans roughly 93 billion light-years from edge to edge. That number is larger than the age of the universe might suggest, because space itself has been expanding the entire time light has been traveling through it. A photon that left a distant galaxy 13 billion years ago has been racing toward us at the speed of light, while the galaxy it came from has been carried away by the expansion of space in the opposite direction. By the time that photon reaches a telescope on Earth, the object that emitted it is no longer where it appears to be. It's more than 40 billion light-years away now, receding faster every second. This is not a theory. This is measurable, observable, repeatedly confirmed reality. And inside that 93 billion light-year bubble, we now know there are at least 2 trillion galaxies. At least. That's the lower bound, the number we're confident about. The actual total could be higher. Nobody knows. What we do know is that the Hubble Space Telescope, the single most successful observatory ever launched, the instrument that spent more than 3 decades staring into the deepest patches of empty sky and pulling back images of galaxies older than dirt, that telescope has seen roughly 10% of what's actually out there. 10%. The rest is invisible. Not because it doesn't exist, not because it's hiding behind something, but because the universe is older, larger, and stranger than the tools we built to look at it were designed to handle. And this brings us to the cosmic web. If you've seen images of the large-scale structure of the universe, the ones that look like a sponge made of light with vast dark voids between glowing filaments, you've seen a cartoon. A useful cartoon, but a cartoon nonetheless. The cosmic web is the name astronomers gave to the way matter is distributed across the universe at the largest scales. Galaxies don't scatter randomly through space like marbles tossed into a pool. They cluster. They line up along invisible threads of dark matter that stretch across hundreds of millions of light years. Where those threads intersect, galaxies pile up into massive clusters containing thousands of individual systems. Between the threads, there's almost nothing, voids. Regions of space so empty that if you stood in the middle of one and looked in every direction, you might see fewer galaxies than you can count on your hands. The cosmic web is not a metaphor. It is the skeleton of the universe. And it formed in the first few 100 million years after the Big Bang, when tiny fluctuations in the density of matter, differences of less than 1 part in 100,000, began to collapse under their own gravity. Dark matter clumped first because it doesn't interact with light or normal matter except through gravity. It just pulls. And as it pulled itself into denser and denser knots, ordinary matter, hydrogen and helium gas, fell into the gravity wells and began to light up. Stars ignited, galaxies assembled. And the structure you see today, the glowing threads and clusters and voids, is the result of nearly 14 billion years of gravity doing exactly what gravity does, pulling things together. The problem is that most of the cosmic web is invisible. The vast majority of its mass is dark matter, which by definition does not emit, absorb, or reflect light. We only know it's there because we can see its gravitational effects on the things that do shine. Galaxies rotating too fast to hold themselves together unless there's extra mass we can't see. Light from distant objects bending around massive clusters in ways that only make sense if there's far more matter present than the visible stars and gas account for. The web itself is a map of dark matter. The galaxies are just the lights we hang on it to see where the threads run. And even those lights, the galaxies themselves, are mostly hidden. This is where the 2 trillion number starts to hurt. When Consolis's team published their findings, they weren't claiming they had seen 2 trillion galaxies. They had seen a fraction of that. What they did was take the galaxies Hubble had detected, analyze their distribution across different distances and brightness levels, and build a model that extrapolated backward to account for the galaxies too faint, too distant, or too obscured to show up in the data. Think of it like standing in a forest at night with a flashlight. You can see the trees closest to you clearly. A little further out, you see shapes, further still, shadows, and beyond that, nothing but black. But you know the forest doesn't stop where your flashlight beam ends. You can estimate how many more trees are out there based on the density of the ones you can see and the size of the forest. That's what Consolis did. Except his forest is 93 billion light-years wide, and his flashlight is the Hubble Space Telescope. The math isn't guessing, it's statistical modeling. The same kind of technique archaeologists use to estimate the total number of artifacts at a dig site based on the density of finds in a small test trench. Consolis called it an intergalactic archaeological dig. And what the dig revealed is that the early universe, the cosmos as it existed in the first few billion years after the Big Bang, was far more crowded than anyone expected. There were 10 times more galaxies per unit of volume back then than there are today. Most of them were small, dwarf galaxies weighing in at around 1 million solar masses. For comparison, the Milky Way weighs roughly 1 trillion solar masses. These early dwarfs were the building blocks. Over billions of years they merged. Gravity pulled them together. Small galaxies collided and stuck, collided again, stuck again. The result is the massive galaxies we see today. The Milky Way, Andromeda, the giant ellipticals sitting at the centers of galaxy clusters, all of them are composites. Frankensteins stitched together from dozens, maybe hundreds, of smaller systems that no longer exist as independent objects. Which means the 2 trillion figure is also a snapshot in time. If you could rewind the universe to a few billion years after the Big Bang and do the same census, you'd count even more galaxies. Smaller ones, yes, but more of them. The total number of galaxies has been dropping for most of cosmic history because mergers reduce the count even as they increase the average size. Concilis pointed this out explicitly. We know that over the 13.7 billion years of cosmic evolution since the Big Bang, galaxies have been growing through star formation and mergers. Significant evolution must have occurred to reduce their number through extensive merging. So when we say 2 trillion galaxies, we're talking about now. Or more precisely, we're talking about the galaxies whose light is reaching us now from all across the history of the universe, each one frozen at whatever moment its light began the journey to Earth. A galaxy 10 billion light-years away isn't being seen as it exists today, it's being seen as it existed 10 billion years ago. We are not looking at a single moment in time. We are looking at a timeline stretched across distance, stitched together into a single image by the fact that light takes time to travel. Now let's talk about why 90% of those galaxies are invisible. The first reason is distance. Light has a speed limit. Nothing in the universe can travel faster. That's not a technological limitation. That's a law. The speed of light in a vacuum is roughly 300,000 kilometers per second, and it has been that speed since the beginning of time, which means that light from the most distant galaxies has been traveling toward us for more than 13 billion years. And over that time, the universe has been expanding. The wavelength of light stretches as space stretches. A photon that started its journey in the ultraviolet part of the spectrum, emitted by hot young stars in a newborn galaxy, arrives at Earth today, shifted all the way into the infrared. This is redshift. The further away a galaxy is, the more its light has been stretched, and the redder it appears. Hubble was designed primarily to observe visible and near ultraviolet light. It has some infrared capability, but not enough to see the most distant galaxies clearly. Those objects are so redshifted that their light falls almost entirely into the infrared spectrum. To Hubble, they're either invisible or so faint they're barely distinguishable from noise. This is why the James Webb Space Telescope was built. Webb observes in the infrared. It was designed specifically to see the galaxies Hubble couldn't, and within months of turning on, Webb started finding them. Galaxies at redshifts of 12, 13, 14, sitting at distances where the universe was less than 500 million years old. Bright, massive, fully formed galaxies that according to the models shouldn't have had time to assemble yet. Webb didn't just confirm the 2 trillion estimate. It validated the idea that there's an entire population of galaxies that previous instruments missed completely because they were looking in the wrong part of the spectrum. The second reason galaxies are invisible is dust. Interstellar dust, the fine particles of carbon, silicon, and metals that float between the stars, absorbs and scatters light. In visible wavelengths, dust can make a galaxy look dim or block it entirely. But infrared light passes through dust much more easily. A galaxy that looks faint and red in visible light because it's choked with dust can shine brightly in the infrared. Webb's ability to peer through dust is one of its most powerful features. It can see into the hearts of star-forming regions, into the cores of distant galaxies, into places that were previously hidden. The third reason is that many galaxies are simply too faint. Low-mass galaxies, the dwarf systems that make up the majority of the early universe's population, don't produce much light. They have fewer stars, and the stars they do have are often older and cooler, meaning they emit less light overall. At large distances, these galaxies fade below the detection threshold of even the most sensitive instruments. They're out there. We know they're out there because the models say they have to be, but we can't see them. Not yet. And then there are the dark galaxies. These are a theoretical class of object that may contain little to no stars at all, just gas. Dark matter holds them together gravitationally, but for whatever reason, star formation never took off. Maybe the gas was too hot. Maybe it was blown out by nearby supernovae before stars could form. Maybe the galaxy formed in a region of space where the conditions just weren't right. We've found hints of these objects. Clouds of hydrogen detected in radio surveys that seem to have mass but no visible counterpart. Gravitational lensing signals that suggest the presence of a massive object where no galaxy appears, but confirming their existence is hard because by definition they don't emit much light. If dark galaxies are common, and some models suggest they could be, they would add significantly to the total count. And they would be completely invisible in optical surveys. You need radio telescopes, gravitational lensing studies, or extremely sensitive infrared observations to even have a chance of detecting them. The cosmic web is held together by dark matter, and if dark galaxies exist, they are the ultimate expression of that. Galaxies made almost entirely of the invisible skeleton of the universe. No lights, just structure. Mapping the invisible 90% is the next frontier. Webb is a start, but it's not enough. Webb can see further and deeper than Hubble, but it's still looking at a tiny fraction of the sky. Its field of view is small. Its observation time is limited. To map 2 trillion galaxies, you'd need thousands of Webbs, all pointed in different directions, running continuously for decades. That's not happening. What is happening is the next generation of ground-based telescopes, the extremely large telescope in Chile with a mirror 39 meters across, the 30-meter telescope if it ever gets built, the giant Magellan telescope. These instruments will have the light-gathering power to detect faint, distant galaxies that Webb can't reach. They'll work in the infrared, cutting through dust and redshift. And they'll have adaptive optics systems that correct for the blurring effects of Earth's atmosphere in real time, producing images nearly as sharp as space telescopes at a fraction of the cost. But even those won't be enough to see everything. The most distant galaxies, the ones at the very edge of the observable universe, are receding from us faster than the speed of light due to the expansion of space itself. That sounds like a contradiction, but it's not. Space can expand faster than light because space isn't a thing. It's the distances between things, and there's no speed limit on how fast distances can grow. What this means is that there is a horizon, a point beyond which light will never reach us no matter how long we wait. Galaxies beyond that horizon are invisible not because our telescopes aren't good enough, but because the photons they emit will never complete the journey. They are outside the observable universe, permanently, forever, and the expansion is accelerating, which means that horizon is getting closer. Galaxies that we can see today will eventually cross that boundary and vanish from view, not because they stopped existing, but because the universe is pulling them away from us faster than their light can catch up. If you wait long enough, trillions of years into the future, observers in our galaxy will look out and see almost nothing. The local group of galaxies, the Milky Way, Andromeda, a few dozen smaller companions, will have merged into a single giant elliptical galaxy. Everything else will have been carried beyond the horizon by the expansion of space. Future astronomers will look at the sky and conclude they live in a universe that contains exactly one galaxy, theirs. They will have no way of knowing that there were ever any others. The evidence will have left the building. This is already happening in reverse. The 2 trillion galaxies we can see now are only the ones whose light has had time to reach us and whose distance hasn't yet carried them beyond the horizon. There are more galaxies out there, many more. The entire universe, not just the observable slice, could be infinite. And if it is, then the number of galaxies is also infinite. 2 trillion is just the number we can, in principle, observe. It's the size of the fishbowl we're swimming in, not the size of the ocean. Consoleist's study was based on data collected over years, piecing together images from multiple telescopes operating at different wavelengths. They converted two-dimensional images, pencil beam surveys that look at narrow slices of sky, into three-dimensional maps by calculating how far away each detected galaxy was based on its redshift. Then they used those maps to estimate the density of galaxies at different distances and extrapolated outward to fill in the gaps. The uncertainties are large, but the conclusion is robust. The universe contains at least 2 trillion galaxies, and most of them are invisible to us. Some because they're too far, some because they're too faint, some because they're hidden by dust, some because they emit light in wavelengths we haven't looked at carefully yet, and some possibly because they don't emit much light at all. The cosmic web is vast, intricate, and mostly dark. What we've mapped so far is a sketch, the faint outline of a structure so large that even light, traveling for 13 billion years, hasn't had time to show us the whole picture. And every galaxy in that structure, every one of those 2 trillion, is not a point of light. It's a city, a collection of hundreds of billions of stars, each with their own planets, their own chemistry, their own chance, however remote, of hosting something that looks up at its own sky and wonders what else is out there. 2 trillion galaxies means something like 200 billion trillion stars. That's a 2 followed by 23 zeros. And around those stars, planets, moons, asteroids, clouds of gas and dust, the raw material for everything. The universe is not empty, it is full to the brim with structure, with history, with possibility, and we've only just begun to see it. We built telescopes, we pointed them at the sky, we counted what we could see and called it a census. Then we built better telescopes and realized we'd miscounted by a factor of 10. The invisible tapestry is still being woven in our minds, thread by thread, galaxy by galaxy, but the fabric itself has been there all along, waiting. And now that we know how much we've been missing, the question isn't whether there are 2 trillion galaxies. The question is, what are they made of? Where did they come from? And how did a universe that started as a cloud of hydrogen and darkness turn itself into something so astonishingly, incomprehensibly full of light? We need to go back to the beginning. Not the comfortable beginning where galaxies already exist and stars are doing their thing and the universe looks more or less like the place we recognize from photographs. The actual beginning. The moment when there was nothing that looked like a galaxy, nothing that looked like a star, and the entire observable universe was smaller than a soccer ball and hotter than any temperature you can imagine without your brain giving up. 13.8 billion years ago, give or take a few tens of millions of years, the universe began, not as an explosion in space, but as an explosion of space itself. Every point in the cosmos expanding outward from every other point simultaneously. There was no center, there was no edge, There was just energy, unimaginable amounts of it, packed into a volume so small that the laws of physics as we understand them today didn't even apply yet. For the first 380,000 years, the universe was a fog, a hot, dense plasma of electrons and protons and photons all bouncing off each other so violently that light couldn't travel more than a fraction of an inch before smacking into something and scattering in a different direction. You couldn't see anything because seeing requires light to travel in straight lines, and light wasn't allowed to do that yet. Then the universe cooled enough for electrons and protons to stick together and form hydrogen atoms. Suddenly, photons had room to move. The fog cleared. Light streamed freely through space for the first time, and that light, stretched and cooled by nearly 14 billion years of cosmic expansion, is what we detect today as the cosmic microwave background, the CMB. The afterglow of creation itself, arriving at Earth as a faint microwave hiss coming from every direction at once, at a temperature of about 2.7 degrees above absolute zero. The CMB is not perfectly smooth. If you map it with enough precision, which the Planck satellite did between 2009 and 2013, you find tiny fluctuations, temperature differences of about 1 part in 100,000, spots that were slightly denser than average, and spots that were slightly less dense. These fluctuations are the seeds, the cosmic DNA. Every galaxy, every cluster, every structure you see in the universe today grew from those tiny wrinkles in the fabric of space-time imprinted in the first fraction of a second after the Big Bang. Here's how it worked. The denser regions had slightly more gravity. Gravity pulled more matter toward them. More matter meant more gravity, and the process fed itself. Over millions of years, the denser patches grew denser while the less dense regions emptied out. The universe began to develop structure. But here's the problem. Ordinary matter, the stuff made of protons and neutrons and electrons, the atoms that make up everything you've ever touched or seen, that matter was still too hot and too energetic to collapse quickly. Radiation pressure kept pushing it around. The photons left over from the Big Bang were still slamming into the hydrogen atoms hard enough to prevent them from clumping together efficiently. Gravity alone wasn't strong enough to overcome that pressure. If the universe had been made only of ordinary matter, galaxies would have taken much, much longer to form. Possibly too long. The tiny density fluctuations in the CMB might have smoothed themselves out before anything interesting happened. Except the universe wasn't made only of ordinary matter. Most of it, roughly 85% of the total mass, was something else. Something that didn't interact with light at all. Something that felt gravity and nothing else. Dark matter. We still don't know what dark matter is made of. We've never directly detected a single particle of it in a laboratory. Every attempt to capture it, and there have been dozens, has come up empty. But we know it's there because we can see what it does. Galaxies rotate too fast to hold themselves together based on the visible matter alone. Galaxy clusters bend light in ways that require far more mass than the stars and gas we can see. And the cosmic microwave background, the map of the early universe, only makes sense if dark matter was already clumping together long before ordinary matter got its act together. Dark matter doesn't bounce off photons. It doesn't feel radiation pressure. It just pulls. And because it was immune to all the forces slowing down ordinary matter, it collapsed first. Within a few tens of millions of years after the Big Bang, dark matter had already formed vast gravitational wells scattered throughout the universe, halos, invisible scaffolds where gravity was strong enough to start pulling in the hydrogen and helium gas drifting through space. Once the gas fell into those halos and cooled enough, it could collapse further. And when it collapsed far enough, The pressure and temperature at the center spiked high enough to ignite nuclear fusion. Hydrogen atoms slammed together, fused into helium, and released energy. Stars turned on, and the first galaxies began to glow. The Standard Model predicted this would take time, hundreds of millions of years, maybe longer, for the first substantial galaxies to assemble. Small proto-galaxies first, dim and irregular, gradually merging and growing into something more organized. The expectation was that if you pointed a telescope at the earliest moments of cosmic history, you'd see faint smudges. Baby galaxies, half-formed clumps of stars, struggling to get their act together in a universe that was still figuring out how to build things. The James Webb Space Telescope turned on in late 2021 and immediately started proving that expectation wrong. Webb was designed specifically to look at the early universe. Its 6.5-meter mirror, coated in gold to reflect infrared light, is the largest ever launched into space. It sits at a gravitationally stable point called L2, about 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and heat. And it observes in the infrared, the wavelength range where the light from the most distant galaxies ends up after being stretched by more than 13 billion years of cosmic expansion. Hubble could see galaxies out to a redshift of about 11, which corresponds to roughly 400 million years after the Big Bang. Beyond that, the galaxies were too faint, too redshifted, and Hubble's instruments hit a wall. Webb was built to smash through that wall, and within months of beginning its science operations, it did. In 2023, Webb's deep field images started coming back, and they were full of galaxies, not faint proto-galaxies, bright ones, massive ones, fully formed spiral and barred structures sitting at redshifts of 12, 13, 14, galaxies seen as they existed just 300 to 500 million years after the Big Bang. Some of them contained as much mass as the Milky Way, or close to it. Some were ablaze with star formation, churning out new stars at rates that made no sense according to the models. One galaxy, officially catalogued as Jade's GSZ 14-0, sits at a redshift of 14.32. The light reaching Webb left that galaxy when the universe was only 290 million years old. It contains hundreds of millions of stars. It spans roughly 1,600 light-years. It is bright enough to be detected across nearly the entire history of the universe, and it has no business existing. To build a galaxy that massive that quickly, nearly every available atom in the surrounding dark matter halo would have had to collapse into stars. In the modern universe, star formation is inefficient. Only about 10% of the available gas in a galaxy ever becomes stars. The rest is too hot, or it gets blown away by supernovae, or it just drifts. But these early galaxies seem to have been running at close to 100% efficiency, like they skipped a step, or like the rules were different back then. Adam Rees, the Nobel Prize-winning astrophysicist who has spent his career measuring the expansion of the universe, looked at the Webb data and said plainly that it suggests we've misunderstood something fundamental. Mike Boylan-Colchin at the University of Texas ran the numbers and found that at least 6 of the earliest galaxies Webb detected are pushing right up against the absolute limit of what the Standard Model of cosmology allows. They shouldn't be there, but they are. So what happened? How do you build a galaxy in 300 million years when the math says it should take twice that long? One possibility is that star formation in the early universe was far more violent and efficient than anything we see today. The first stars, the ones astronomers call population 3 stars, were monsters. They were made entirely of hydrogen and helium because nothing else existed yet. No carbon, no oxygen, no metals. In modern stars, heavier elements help cool the gas clouds during collapse, allowing smaller stars to form. Without those elements, the first stars couldn't cool efficiently. They collapsed into enormous masses, possibly hundreds of times heavier than the Sun, burning blue hot and dying in just a few million years in catastrophic supernovae that seeded the surrounding space with the first heavy elements. If the early universe was dominated by these short-lived giants, star formation could have proceeded much faster than current models assume. Instead of taking hundreds of millions of years to build up a substantial population of stars, early galaxies might have ignited in bursts, stellar wildfires, entire molecular clouds collapsing at once, forming thousands or tens of thousands of massive stars in a single event, each one burning furiously and dying young, enriching the gas for the next generation. Another possibility is that dark matter behaved differently in the early universe. The standard cosmological model assumes that dark matter is cold, meaning its particles move slowly relative to the speed of light. Cold dark matter clumps efficiently and forms the gravitational scaffolding for galaxies. But if dark matter was slightly warmer, or if it interacted with itself in ways we haven't accounted for, the halos could have formed faster or been denser than the models predict. That would give ordinary matter a head start, pulling it into tighter clumps more quickly and allowing stars to ignite sooner. A third possibility, and this one is gaining traction, is that some of the bright objects Webb is seeing aren't galaxies in the traditional sense at all. They might be powered by supermassive black holes, quasars. Accreting black holes can outshine entire galaxies because the gas spiraling into them heats up to millions of degrees and radiates furiously across the electromagnetic spectrum. If supermassive black holes formed very early, possibly through direct collapse of massive gas clouds that skipped the stellar phase entirely, they could have been lighting up the early universe in ways that look like large galaxies but are actually something else. This isn't speculation pulled out of thin air. We already know that supermassive black holes existed less than 1 billion years after the Big Bang because we've detected their quasars. The problem is that the standard model struggles to explain how black holes weighing millions or even billions of solar masses could have grown that large that fast, starting from stellar mass seeds left behind by the first supernovae. There simply wasn't enough time. But a direct collapse black hole, one that formed at 100,000 solar masses or more in a single event, would have a massive head start. And if those objects were common in the early universe, the bright light Webb is detecting from some of these early galaxies might be coming from their central black holes rather than from billions of stars. We don't know yet. The data is still too new. The observations are still being analyzed, but the pattern is clear. The early universe was not the slow, cautious place the models predicted. It was fast, it was efficient, it was building cities of stars while the cosmos was still in diapers. The process of galaxy formation, as we understand it today, starts with those dark matter halos. Picture a vast, invisible cloud, roughly 1 million light-years across, made of particles that don't emit light and don't collide with anything except through gravity. The cloud slowly collapses under its own weight, growing denser at the center. Hydrogen and helium gas, the primordial stuff left over from the Big Bang, falls into the halo and begins to swirl. The gas heats up as it falls, but it also radiates that heat away as infrared light, cooling, collapsing further. Eventually, dense pockets of gas within the halo reach the critical threshold. The core temperature climbs above 10 million degrees Kelvin. Hydrogen nuclei, protons, overcome their electromagnetic repulsion and fuse into helium. Energy floods outward, a star is born, then another, then thousands. The first generation lights up the halo from within, ionizing the surrounding gas, blowing bubbles of hot plasma outward with their radiation and stellar winds. Massive stars explode as supernovae, scattering heavy elements into the interstellar medium. Carbon, oxygen, nitrogen, iron, the building blocks of planets and, eventually, life. The second generation of stars forms from gas enriched with those heavy elements. They're smaller, longer-lived, more stable. Rocky planets can form around them, and over hundreds of millions of years, the galaxy takes shape. The gas settles into a rotating disk if the halo has enough angular momentum. Stars orbit the center in roughly circular paths. Spiral arms form, regions where gas piles up due to density waves moving through the disk like traffic jams on a highway. If the galaxy experiences a major merger early on, something smashes into it and disrupts the disk. The stars get scrambled into a more chaotic distribution, an elliptical galaxy, smooth, featureless, no spiral arms, no organized disk, just a swarm of stars orbiting the center in random directions. Irregular galaxies, the ones that don't fit neatly into spirals or ellipticals, are usually the result of gravitational interactions. Something tugged on them, tidal forces stretched them out, or they're just small systems that never accumulated enough mass to settle into a stable configuration. Most of the galaxies in the early universe were probably irregular, small, chaotic, full of star formation, but lacking the organized structure we see in mature galaxies like the Milky Way or Andromeda. Over time, galaxies grow by eating each other. Small galaxies fall into larger ones. The Milky Way has about 60 known satellite galaxies orbiting it right now, most of them tiny dwarf systems containing only a few million stars. And we know from the motion of stars in the Milky Way's halo that our galaxy has already consumed dozens of smaller galaxies over its lifetime. You can still see the debris, streams of stars stretched out in long arcs, the remnants of dwarf galaxies that were torn apart by tidal forces as they spiraled inward and merged with the main disk. This process of hierarchical assembly, small things merging into bigger things over billions of years, is the backbone of galaxy evolution. The 2 trillion galaxies we can see today are the survivors. Most of the galaxies that existed in the early universe no longer exist as independent objects. They've been incorporated into larger systems. The total number of galaxies has been dropping for most of cosmic history, even as the average mass has been going up. But here's the thing, the Webb data suggests that even in the earliest moments, some galaxies weren't starting small, some of them were born big, or they grew big so fast that the difference doesn't matter. And that breaks the story we've been telling ourselves about how this process works. Christopher Consolis, the astronomer who led the 2016 study that revised the galaxy count from 100 billion to 2 trillion, described the work as an intergalactic archaeological dig. You're looking at objects billions of light years away, which means you're seeing them as they were billions of years ago. The further you look, the further back in time you see. And by comparing the number and types of galaxies at different distances, you can reconstruct the history of how they assembled. What that reconstruction showed is that the early universe, a few billion years after the Big Bang, was far more crowded than today. There were 10 times more galaxies per unit of volume back then. Most of them were small, but there were a lot of them. And over time, mergers reduced the count. The big ate the small merged with each other and became medium. The medium collided with other medium galaxies and became large, and the large systems, the spirals and giant ellipticals we see dominating galaxy clusters today, are the endpoint of that process. For now, but the Webb galaxies, the ones forming just 300 million years after the Big Bang, don't fit that timeline comfortably. They skipped steps. or the steps happened faster than we thought possible, and nobody has a complete explanation yet. The density fluctuations in the cosmic microwave background, the tiny wrinkles that seeded galaxy formation, are well understood. We've measured them to extraordinary precision. The physics of how dark matter clumps together is solid. The equations work. But somewhere between the CMB at 380,000 years and the first massive galaxies at 300 million years, something happened that the models didn't predict. The universe found a shortcut. Some researchers think the answer lies in the nature of the first dark matter halos. If they were denser than expected, or if they formed in regions of space where the initial density fluctuations were higher than average, the collapse could have been faster. Others point to the efficiency of star formation. If the first molecular clouds converted gas into stars at rates far higher than what we see in the modern universe, you could build a massive galaxy in a fraction of the time, and still others are revisiting the role of black holes. If supermassive black holes formed early and grew fast, they could have influenced the surrounding gas in ways that accelerated star formation, triggering bursts of activity that built up stellar populations much more quickly than a steady, gradual process ever could. All three explanations might be true at once. The early universe might have been a perfect storm of conditions that we don't see anymore. Denser halos, hotter gas, more efficient collapse, black holes seeding galaxies from the inside out, a chaotic, violent, creative phase of cosmic history that set the stage for everything that came after. The galaxies we see today, the spirals and ellipticals and irregulars, are not the same as the galaxies that first formed. They're the descendants, edited by billions of years of mergers, star formation, supernovae, black hole feedback, and gravitational interactions. The Milky Way itself is a composite, a Frankenstein's monster stitched together from hundreds of smaller systems that no longer exist. Every star in our galaxy has a history. Some were born here. Some arrived as refugees from dwarf galaxies that got too close and were torn apart. The stars in the galactic halo, the faint, sparse population surrounding the disk, are mostly immigrants, orphans from dead galaxies, and this process is still happening. Right now, the Milky Way is in the process of cannibalizing the Sagittarius dwarf elliptical galaxy, a small system that's been looping around us for billions of years, shedding stars every time it passes through our disk. In a few billion years, it will be gone, dissolved. Its stars will be part of us, and we won't even remember it was ever separate. In about 4 billion years, the Milky Way will collide with Andromeda, our nearest large neighbor. The two galaxies will pass through each other, their stars missing each other by vast distances because space is mostly empty, but their gravitational fields tangling together like hair in a drain. Over the course of a few billion years, the two galaxies will merge. The result will be a giant elliptical galaxy, smooth and featureless, all the gas used up or blown away, star formation mostly finished. Astronomers have already named it Milkomeda. By that time, anyone's still around to see it, and there's no guarantee anyone will look up at a sky full of stars from both galaxies mixed together into a single swarm. The spiral arms will be gone, the disk will be scrambled, and the night sky will be unrecognizable. This is the story of galactic genesis. It starts with quantum fluctuations in the first fraction of a second after the Big Bang. Tiny wrinkles in space-time that grew into the seeds of everything. Dark matter collapsed first, building the invisible scaffolding. Ordinary matter fell into the wells, cooled, collapsed, and ignited. Stars formed, galaxies assembled, some quickly, some slowly, but all of them following the same fundamental process. Gravity pulls things together, and once you have enough mass in one place, the universe finds a way to light it up. The James Webb Space Telescope has shown us that the process was faster, messier, and more violent than we expected. The early universe was not patient. It did not wait for the models to catch up. It built galaxies while the cosmos was still figuring out its own rules. And now, 13.8 billion years later, we're standing on a planet orbiting a star in one of those galaxies, pointing instruments back at the beginning, trying to piece together how we got here. The galaxies themselves are not static. They're dynamic, evolving, feeding, growing, colliding, dying. Every one of those 2 trillion galaxies has a history, a birth, a middle age, and eventually an end. And at the heart of nearly every one, something waits that shouldn't exist at all. Something so dense, so massive, that it bends space-time into a knot, a place where the rules break down completely. We call them supermassive black holes, and they didn't just form inside galaxies. In many cases, they built the galaxies around them. We've been talking about galaxies as if they're passive objects, collections of stars that formed, settled into place, and just sort of sit there glowing politely while the universe ages around them. That picture is wrong. Galaxies are violent, dynamic, actively regulated systems, and at the center of nearly every large galaxy in the observable universe, there's a mouth. A gravitational singularity so massive and so dense that it warps space-time into a funnel with no bottom. A supermassive black hole. And that object is not just sitting there, it's controlling everything. The Milky Way has one. We've known this since the 1990s, but the evidence has gotten sharper every year. Sagittarius, a star, the radio source sitting at the exact center of our galaxy, roughly 26,000 light-years from Earth. For decades, astronomers tracked the motion of stars orbiting close to it, stars moving so fast that they complete full orbits in just a few years. One star, called S2, swings around Sagittarius A star in an ellipse so tight that at closest approach it's moving at nearly 3% the speed of light. 3%. You don't get speeds like that unless there's an enormous amount of mass packed into a very small volume, and the only thing that fits the data is a black hole weighing about 4.3 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. In May of 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star. Not the black hole itself, because by definition black holes don't emit light, but the glowing ring of superheated gas swirling around it just outside the event horizon. The image looks almost identical to the one they released 3 years earlier of the much larger black hole at the center of the galaxy M87, a bright orange ring surrounding a dark circle, the shadow of the event horizon. Proof that what we've been inferring from stellar orbits and radio emissions for decades is exactly what we thought it was. A supermassive black hole sitting at the gravitational center of the galaxy, holding everything in orbit around it. And the Milky Way's black hole is small. On the scale of supermassive black holes, 4 million solar masses barely registers. There are black holes out there that make Sagittarius A star look like a marble next to a planet. TON 618. Discovered in 1957 as a faint blue object in photographic sky surveys, misidentified as a star for 15 years until beta spectroscopy revealed it was actually a quasar sitting more than 10 billion light-years away. The light we see from TON 618 left when the universe was less than 4 billion years old, and the black hole powering that quasar weighs roughly 66 billion times the mass of our Sun. 66 billion. Some more recent estimates put it closer to 40 billion, but either number is absurd. The event horizon of that black hole stretches more than 1,300 astronomical units in radius. That's more than 30 times the distance from the Sun to Pluto. light takes 2 weeks to cross. Phoenix, a star, sitting at the center of the Phoenix cluster, about 5.7 billion light-years away, weighs in at roughly 40 billion solar masses, and there are dozens more in the same weight class scattered across the observable universe. These objects didn't just form at that size, they grew, starting from something much smaller and feeding for billions of years on everything that fell into their gravity wells. There are 3 ways a supermassive black hole grows. The first is accretion. Gas, dust, stars, anything with mass that gets too close and doesn't have enough velocity to escape falls inward, but it doesn't fall straight in. Conservation of angular momentum means that in falling material spirals into a rotating disk around the black hole, an accretion disk, where friction between particles heats the gas to millions of degrees, hot enough to glow, hot enough to emit X-rays. The closer the gas gets to the event horizon, the faster it moves and the hotter it gets. At the innermost edge of the disk, just before the material crosses the point of no return, it's moving at a significant fraction of the speed of light and radiating more energy per gram than a nuclear bomb. This is where quasars come from, the brightest objects in the universe. A quasar is just a supermassive black hole feeding so aggressively that the light from its accretion disk outshines every star in the galaxy around it. The first quasar ever identified, 3C273, was catalogued in 1963. Astronomers thought it was a star in our own galaxy until they measured its redshift and realized it was sitting more than 2 billion light-years away. For it to be visible at that distance and still appear as bright as it did, it had to be emitting more energy than 100 Milky Way galaxies combined. All of that power coming from a region smaller than our solar system. We know now that roughly 1% of galaxies in the nearby universe are actively feeding their central black holes at rates high enough to qualify as active galactic nuclei, AGN. But in the early universe, the fraction was much higher, at redshifts greater than 6, corresponding to less than a billion years after the Big Bang. Something like 30% of galaxies were active. The early universe was a feeding frenzy. Gas was more abundant, galaxies were colliding more often, and supermassive black holes were growing as fast as physics would allow. There's a theoretical speed limit to how fast a black hole can grow by accretion. It's called the Eddington limit, named after Arthur Eddington, the British astrophysicist who first worked out the balance between radiation pressure and gravity in stars. The idea is simple. As gas falls into a black hole and heats up, it radiates. That radiation pushes outward on the surrounding gas. If the black hole is feeding too fast, the outward pressure from the radiation becomes strong enough to blow away the infalling material. The gas gets pushed back before it can cross the event horizon. The Eddington limit is the point where the inward pull of gravity exactly balances the outward push of radiation pressure. For a black hole feeding at the Eddington limit, its mass roughly doubles every few tens of millions of years. That sounds fast. It isn't. Not when you're trying to grow a billion solar mass black hole in less than a billion years, starting from a stellar mass seed left behind by a supernova. Run the numbers and it doesn't work. There simply isn't enough time. Even if a black hole fed continuously at the Eddington limit from the moment the first stars died, which is unlikely because gas doesn't just queue up politely waiting to fall in, you can't grow something the size of the black holes we see in the early universe that quickly. Which brings us to the second way black holes grow: mergers. When two galaxies collide, and they do collide, frequently their central black holes eventually spiral toward each other and merge. The process takes a long time, hundreds of millions of years. The black holes start out separated by thousands of light years, orbiting each other at a distance, dragging streams of stars and gas along with them. Gradually, Interactions with surrounding matter sap energy from their orbits and they drift closer. When they get within a few light years of each other, they start radiating gravitational waves, ripples in space-time itself that carry away orbital energy. The closer they get, the faster they spiral, and the stronger the gravitational waves become. At the final moment, when the event horizons touch, they merge in a fraction of a second, releasing more energy in gravitational waves than all the stars in the observable universe emit as light during that same fraction of a second. We've detected those mergers. The Laser Interferometer Gravitational Wave Observatory, LIGO, started picking up signals from merging black holes in 2015. Most of the ones they've found are stellar mass black holes, a few dozen solar masses each. But in 2023, pulsar timing arrays, networks of radio telescopes monitoring the precise ticking of pulsars scattered across the galaxy, detected the faint background hum of gravitational waves at much lower frequencies. The signal is consistent with thousands of supermassive black hole mergers happening across the universe at any given moment, their combined gravitational wave output blending together into a low-frequency background noise that permeates space-time. Every time two supermassive black holes merge, the resulting black hole weighs slightly less than the sum of the two originals. The missing mass gets radiated away as gravitational waves, but the process still adds up. Mergers can double a black hole's mass in less than 1 billion years if the host galaxy is in a dense environment where collisions are common, and in the early universe they were. The third mechanism is direct stellar capture. A star wanders too close to the black hole, crosses the tidal radius, the point where the difference in gravitational pull between the near side and the far side of the star becomes strong enough to rip it apart, and the star gets shredded. We call these events tidal disruption events. The star doesn't fall in whole. It gets stretched into a long stream of gas, half of which falls into the black hole and half of which gets flung outward at high speed. The infalling gas heats up and glows brightly in X-rays for a few weeks or months before fading. Astronomers have been catching these events in real time for the past couple of decades. They're rare, maybe one per galaxy per 10,000 years, but when they happen, they're spectacular. Stellar capture doesn't contribute much to a black hole's overall growth. Stars are tiny compared to the amount of gas floating around in a galaxy, but it adds up over billions of years. And in the dense cores of galaxies, where stars are packed closer together than anywhere else, the occasional unlucky star gets too close and disappears. Put all three mechanisms together, accretion, mergers, and stellar capture, and you can grow a supermassive black hole from a stellar mass seed, 10 or 20 solar masses, up to millions or billions of solar masses over the lifetime of the universe. Probably. The math works if you assume the black hole is feeding efficiently and merging regularly, but the black holes we're finding in the early universe are testing that assumption. The James Webb Space Telescope has now detected supermassive black holes weighing 1 billion solar masses or more at redshifts greater than 10, less than 500 million years after the Big Bang. To grow that massive that fast, they would have had to start much larger than a stellar mass seed, which means something else was happening. The leading idea is called direct collapse. In the early universe, under specific conditions, a massive cloud of primordial gas could have collapsed straight into a black hole without ever forming stars. No supernovae, no stellar remnants, just 100,000 solar masses of gas collapsing directly into a black hole in one event. If that happened, and there are simulations suggesting it could have, those black holes would have had an enormous head start. Grow 100,000 solar mass black hole at the Eddington limit for a few 100 million years, and you can reach 1 billion solar masses. The timeline fits. Barely. Webb's data from 2023 and 2024 strongly suggests that direct collapse, or something like it, must have happened. The alternative is that the standard model of black hole growth is missing something fundamental. Either way, the early universe was building supermassive black holes faster than it should have been able to, and those black holes were lighting up their galaxies in ways that changed everything. This is where the story gets interesting, because supermassive black holes don't just sit at the centers of galaxies growing quietly and minding their own business. They talk back. They influence, regulate, and in many cases, completely dominate the evolution of the galaxies around them. The key is something astronomers call feedback. When a supermassive black hole is actively accreting, feeding on gas from its surroundings, a significant fraction of the energy released by the infalling material doesn't fall into the black hole. It gets radiated outward or flung away in powerful jets and winds. Active galactic nuclei, the galaxies with rapidly feeding black holes, emit radiation across the entire electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared, radio waves. That radiation slams into the surrounding gas, heating it, ionizing it, and in many cases pushing it outward so hard that it escapes the galaxy entirely. The jets are even more dramatic. Some supermassive black holes, particularly the ones in giant elliptical galaxies, fire narrow beams of plasma out along their rotation axes at speeds close to the speed of light. The jet from the black hole at the center of M87, the one the Event Horizon Telescope imaged in 2019, extends for more than 5,000 light-years, glowing brightly in radio wavelengths. These jets plow through the intergalactic medium, carving out enormous cavities, bubbles of hot gas that can span hundreds of thousands of light-years. The energy deposited by those jets heats the surrounding gas so much that it can't cool down and collapse to form new stars. This is the feedback loop. The black hole accretes gas. The accretion releases energy. The energy heats and expels gas from the galaxy. Less gas means less fuel for star formation. Star formation slows or stops entirely. The galaxy transitions from a blue, actively star-forming system to a red, quiescent one. And the black hole, having eaten or expelled most of the available gas, goes quiet. It stops feeding. The galaxy stabilizes. This process regulates the growth of both the galaxy and the black hole, and it's why the two are so tightly linked. In 1998, astronomers John Cormendy and Douglas Richton published one of the first clear demonstrations of this link. They showed that the mass of a galaxy's central black hole correlates almost perfectly with the mass of the galaxy's stellar bulge, the dense central region of old stars. Bigger bulge, bigger black hole. The ratio is roughly 1 to 200. For every 200 solar masses of stars in the bulge, there's about 1 solar mass in the black hole. That relationship, refined over the years and now known as the M-sigma relation because it links black hole mass to the velocity dispersion of stars in the bulge, holds across more than 5 orders of magnitude in black hole mass, from millions to tens of billions of solar masses. It's one of the tightest correlations in all of astrophysics. Why does it exist? The black hole contains less than 1% of the total mass of the galaxy. It's a tiny fraction of the system. It shouldn't have any influence on the other 99%, except it does, because the energy it releases when it feeds is enormous, and that energy couples to the gas in the galaxy, heating it, moving it, and ultimately controlling how much of it can collapse to form stars. The black hole and the galaxy grow together. When the galaxy merges with another galaxy, fresh gas falls toward the center. The black hole feeds, star formation ignites, and the feedback eventually shuts both processes down. The galaxy and the black hole reach a new equilibrium, slightly more massive than before, and the cycle starts again. Priyamvada Natarajan, a theoretical astrophysicist at Yale who has spent much of her career modeling black hole growth, put it plainly: no supermassive black hole sits in isolation. It's the beating heart of its galaxy. The black hole doesn't just respond to its environment, it shapes it. The stars, the gas, the structure of the galaxy itself are all influenced by the central engine. In many massive galaxies, the black hole is the single most important factor determining whether the galaxy is still forming stars or whether it's finished. The evidence for this is everywhere. Look at the most massive galaxies in the universe, the giant ellipticals sitting at the centers of galaxy clusters. They're red, they're smooth, they have almost no gas left and almost no star formation. Their central black holes are enormous, billions of solar masses, and those black holes have spent billions of years pumping energy into the surrounding gas, keeping it too hot to collapse. The Silk and Rees model, published in 1998, predicted exactly this. The black hole grows until its feedback energy becomes strong enough to unbind the gas from the galaxy. At that point, the galaxy stops growing. The black hole stops growing, and the system reaches what's called a quenched state. About 70 to 90% of the gas in the most massive galaxies has been expelled or heated to temperatures where it can't form stars, and black hole feedback is the most likely culprit. Supernovae contribute, yes, but they don't have the reach. A supernova explosion can blow gas out of a small region, a few hundred light-years across. A supermassive black hole can influence the entire galaxy, hundreds of thousands of light-years, because the energy it releases is centralized and continuous. One massive black hole feeding for a few million years can pump more energy into a galaxy than a billion supernovae combined. Andrea Ghez, who won the Nobel Prize in 2020 for her work mapping the orbits of stars around Sagittarius, a star, once said that black holes are where God divided by zero. The laws of physics, as we understand them, break down completely at the singularity. But outside the event horizon, in the region where the black hole interacts with the rest of the universe, the physics is clear: gravity pulls things in. Accretion releases energy. Energy regulates the galaxy, and the result is a universe full of galaxies that are not independent systems. They're ecosystems, feedback loops. The black hole feeds the galaxy by destroying stars and enriching the gas with heavy elements. The galaxy feeds the black hole by funneling gas inward during mergers and gravitational interactions. And the two grow together, locked in a dance that's been going on for more than 13 billion years. The James Webb Space Telescope has added a new wrinkle to this story. The supermassive black holes it's finding at redshifts of 10 and higher, black holes that shouldn't exist yet according to the old models, are sitting in galaxies that are also too massive and too mature for their age. The correlation holds even in the earliest moments of cosmic history, which means the feedback loop was already running less than 500 million years after the Big Bang. The black holes formed early, possibly through direct collapse, and immediately started regulating their host galaxies. The process didn't wait for the universe to settle down. It was baked in from the start. There's a chicken and egg problem here that nobody has fully solved. Did the black holes form first and build the galaxies around them? Or did the galaxies form first and grow the black holes? The M-sigma relation suggests they grew together, but the Webb data is pointing towards scenarios where the black holes got a head start. If direct collapse is real, and 100,000 solar mass black hole can form in a single event before the first stars even finish their lives, then the black hole could have been there first, pulling in gas, igniting star formation, and sculpting the galaxy from the inside out. That's not the story we've been telling for the past few decades. The standard model assumed galaxies formed first, stars died, and stellar mass black holes grew slowly into supermassive ones over billions of years. But the data keeps pushing us toward a different picture, one where supermassive black holes are not the product of galaxy evolution. They're the cause of it, the engine that drives everything else. And if that's true, then every galaxy we see, every one of those 2 trillion, is the result of a balancing act between gravity trying to pull gas inward and black hole feedback trying to blow it away. The ones that survive, the ones that grow into massive spirals or giant ellipticals, are the ones where that balance held long enough for stars to form and structure to develop. The ones where the balance tipped too far in either direction, too much infall or too much feedback, either collapsed into something unrecognizable or blew themselves apart before they could build anything lasting. The Milky Way is still in balance. Sagittarius, a star, is quiet right now. It's not accreting much. There's no active galactic nucleus, no quasar blazing away at the center of our galaxy. Just a dormant black hole, 4 million solar masses, sitting at the gravitational center, holding 200 billion stars in orbit around it. But that wasn't always the case. There's evidence, X-ray emissions and gamma-ray bubbles extending thousands of light-years above and below the galactic disk, that Sagittarius A star was active a few million years ago. It fed, it flared. It blew gas outward in a powerful wind that we can still detect today, and it will probably feed again. In a few billion years, when the Milky Way collides with Andromeda, gas will funnel toward both central black holes. They'll light up. The combined system will briefly become an active galactic nucleus, possibly even a quasar, shining brightly enough to be visible across billions of light years. Then the black holes will merge, the feedback will expel most of the remaining gas, and the system will go quiet again. A giant elliptical galaxy with a monstrous black hole at its center, slowly fading as the last of its stars age and die. That's the fate of most galaxies. Merge, feed, flare, quench, fade. And at every step, the supermassive black hole is there, controlling the process, regulating the flow of gas, determining how many stars form and how long the galaxy stays active. The hearts of giants are not passive. They're the most powerful engines in the universe, and they've been running since the very beginning. The galaxies we've been talking about, the ones forming stars, growing, assembling into the structures we see today, they don't do any of that in isolation. They collide, they merge, they tear each other apart and build something new from the wreckage. And when they do, their central black holes come along for the ride. The galaxies we've been talking about, the ones forming stars, growing, assembling into the structures we see today, they don't do any of that in isolation. They collide, they merge, they tear each other apart and build something new from the wreckage. And when they do, their central black holes come along for the ride. Galaxy collisions are not rare. They are not cosmic accidents. They are the primary mechanism by which galaxies grow. The universe has been running a continuous demolition derby for more than 13 billion years, and the 2 trillion galaxies we can count today are just the survivors, the ones still standing. Most of the galaxies that existed in the early universe no longer exist as independent objects. They've been absorbed, cannibalized, stitched together into larger systems that remember nothing about where their stars originally came from. Christopher Consolis, the astronomer whose team revised the galaxy count in 2016, put it plainly. Finding more galaxies in the past implies significant evolution must have occurred to reduce their number through extensive merging. The total count has been dropping for most of cosmic history. 10 billion years ago, the universe had roughly 10 times more galaxies per unit volume than it has today. Most of them were small, dwarf galaxies weighing in at around 1 million solar masses, tiny by modern standards, but there were a lot of them, and over billions of years they collided. They stuck together. The small merged into medium. The medium merged into large. And the large systems, the spirals and giant ellipticals we see dominating the modern universe, are composites, Frankensteins built from hundreds of smaller galaxies that no longer exist. The Milky Way itself is one of those composites. You are standing on a planet orbiting a star in a galaxy that is the product of dozens, possibly hundreds of past collisions. We know this because we can still see the debris. Stellar streams, long arcs of stars stretched across the sky, the remnants of dwarf galaxies that wandered too close and got torn apart by tidal forces. The Sagittarius stream is one of the most prominent, a ribbon of stars wrapping around the Milky Way multiple times, the shredded remains of the Sagittarius dwarf elliptical galaxy, a small system that's been looping around us for billions of years, losing a little more of itself with each pass. In a few billion years, it will be gone completely, dissolved. Its stars will be indistinguishable from the rest of the Milky Way's halo. The Orphan stream is another one. The Helmi stream, the Monoceros ring. Each one is the corpse of a dwarf galaxy that fell into our gravity well and didn't make it out. The European Space Agency's Gaia satellite, which has been mapping the positions and velocities of more than 1 billion stars in the Milky Way since 2013, has revealed that roughly a third of the stars in our galaxy's halo didn't form here. They're immigrants, refugees from smaller galaxies that merged with us over the past 10 billion years. The biggest merger the Milky Way ever experienced happened roughly 10 billion years ago. Astronomers call it Gaia Enceladus. A dwarf galaxy about 1/10 the mass of the Milky Way at the time slammed into us, disrupted the disk, scattered billions of stars into the halo, and dumped its entire stellar population into our system. The collision was violent enough to leave a signature in the orbits of stars that we can still detect today. Thousands of stars moving in strange directions, all of them tracing back to the same event, a galactic hit and run from the distant past. And that wasn't even the last one. Right now, at this moment, the Milky Way is in the process of absorbing the Large Magellanic Cloud, a dwarf galaxy about 1/20th our mass, sitting about 160,000 light-years away, slowly spiraling inward. In a few billion years, it will collide with the Milky Way's disk, trigger a burst of star formation, and merge. The stars in the Large Magellanic Cloud, the ones you can see with the naked eye if you're standing in the southern hemisphere, will eventually become part of us. Their stars will orbit our center. Their gas will fuel our star formation. And nobody looking at the night sky a few billion years from now will have any way of knowing they were ever separate. Galaxy mergers follow a predictable pattern. It starts with gravity. Two galaxies pass close enough that their gravitational fields begin to interact. At first, nothing dramatic happens. The galaxies are still separated by hundreds of thousands of light years, but gravity is patient. The pull is always there, always tugging, and over tens or hundreds of millions of years, the galaxies drift closer. As they approach, tidal forces start to distort them. Tidal forces are just the difference in gravitational pull between the near side of an object and the far side. The side of one galaxy facing the other feels a stronger pull than the side facing away. The result is stretching. The galaxies develop long tails of stars and gas streaming out behind them like hair in the wind. The Hubble Space Telescope has captured dozens of these systems in progress. The antennae galaxies are the most famous example. Two spiral galaxies, NGC 438 and NGC 4439, about 45 million light-years from Earth, currently in the process of merging. They've already passed through each other once. The collision scrambled their disks and flung out two long tidal tails that stretch for hundreds of thousands of light-years. The tails glow with young stars, regions where the gas compressed during the collision and ignited. The James Webb Space Telescope imaged the antennae Galaxies in 2023 and found something Hubble missed. Buried deep in the cores, hidden by dust in visible wavelengths, there are massive clusters of newborn stars. Some of them contain more than 1 million solar masses of stars packed into regions only a few hundred light-years across. Superstar clusters, the kind of environment where stars form so close together that their light blends into a single continuous glow. These clusters are being born directly from the chaos of the collision. Gas from both galaxies funneled into the cores, compressed, and ignited all at once. This is the starburst phase. During a galactic merger, especially between gas-rich spiral galaxies, the collision compresses the interstellar medium, the clouds of hydrogen and helium drifting between the stars. Compression increases density. Increased density leads to collapse, and collapse leads to star formation, a lot of star formation. Starburst galaxies can produce stars at rates 10 to 100 times higher than normal galaxies. For a few tens of millions of years, the merger becomes one of the brightest objects in the local universe, blazing away in ultraviolet and infrared light as millions of massive young stars ignite and flood the system with radiation. But starbursts don't last. Massive stars burn fast and die young. Within a few million years, the first generation of stars born in the collision goes supernova. Those explosions blow gas out of the galaxy, heating what's left to temperatures so high it can't collapse anymore. Star formation slows, then stops, and the galaxy transitions from a bright blue actively star-forming system to a red quiescent one. The merger is over. What's left is a single galaxy, usually an elliptical, smooth and featureless, all its gas either consumed or expelled, sitting quietly in space with no fuel left to do much of anything. The process takes time, 1 billion years, sometimes longer depending on the masses involved and the angle of the collision. But the outcome is predictable. Two spirals collide, they lose their structure, the disks get scrambled. The spiral arms disappear. The stars settle into a more chaotic distribution, orbiting the center in random directions rather than in the organized disk they started in. And what you're left with is an elliptical galaxy. This is how most ellipticals form. They're not a separate type of galaxy that evolved on their own. They're the wreckage of spiral galaxies that collided and merged. And then there are the black holes. Every large galaxy has a supermassive black hole at its center. When two galaxies merge, their black holes come along. At first, they're separated by the same distance as the galactic cores, thousands of light-years. But as the galaxies spiral inward and the stars and gas settle, the black holes drift toward the center of the combined system. They form what astronomers call a binary black hole. Two supermassive black holes orbiting each other, locked in a slow death spiral that will eventually end with them merging into a single, even more massive black hole. The in-spiral takes a long time, hundreds of millions of years. The black holes start out orbiting each other at a distance where their gravitational influence on the surrounding stars and gas is enough to sap energy from their orbits. Slowly, stars pass close to the binary, get flung outward at high speed, and in the process steal a tiny bit of orbital energy from the black holes. This is called the three-body problem, and it's one of the messiest bits of orbital mechanics in astrophysics. But it works. Over time, the black holes lose energy, they drift closer, their orbit tightens. When they get within a few light-years of each other, stars can't sap energy fast enough to keep the in-spiral going. The process stalls. Astronomers call this the final parsec problem. A parsec is about 3¼ light years. The final parsec is the distance at which the black holes are close enough that they should merge quickly, but the mechanism that brought them that close stops working. For years, this was a theoretical roadblock. Nobody knew how the black holes crossed the final parsec. Then in 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected the first direct evidence of merging black holes, not supermassive ones, stellar mass black holes, a few dozen solar masses each, but the detection proved that black holes do merge, and it gave physicists the tool they needed to solve the final parsec problem: gravitational waves. As the black holes get closer, they start radiating gravitational waves, ripples in space-time itself that carry away energy and angular momentum. The closer they get, the faster they orbit, and the stronger the gravitational waves become. By the time the event horizons touch, they're radiating more energy in gravitational waves than all the stars in the observable universe emit as light during that same moment. The merger itself takes a fraction of a second. The two black holes collide, the event horizons merge, and the resulting black hole rings like a struck bell, emitting a final burst of gravitational waves before settling into a stable configuration. In 2023, pulsar timing arrays, networks of radio telescopes monitoring the precise ticking of pulsars scattered across the galaxy, detected something remarkable: a faint background hum of gravitational waves at much lower frequencies than LIGO can detect. The signal is consistent with thousands of supermassive black hole mergers happening across the universe at any given moment, their combined gravitational wave output blending together into a low-frequency background noise that permeates space-time. We are, quite literally, swimming in the ripples of black hole collisions happening billions of light-years away. Every galaxy merger eventually ends with a black hole merger, and every black hole merger adds to the mass of the central engine. This is one of the primary ways supermassive black holes grow, not by accreting gas, though that happens too, but by merging with other supermassive black holes. The black hole at the center of a giant elliptical galaxy sitting in a massive galaxy cluster didn't start out weighing tens of billions of solar masses. It grew, merger by merger, galaxy by galaxy, over billions of years. Now let's talk about what's coming, because the Milky Way is not done merging. The largest galaxy in our local neighborhood, Andromeda, also called M31, is heading toward us. And in about 4 to 5 billion years, we're going to collide. Andromeda is roughly 2.5 million light-years away. It's the most distant object you can see with the naked eye, a faint smudge in the autumn sky in the northern hemisphere. But it's not staying put. Andromeda is moving toward the Milky Way at about 110 kilometers per second. That's not unusual. Galaxies move. The expansion of the universe carries distant galaxies away from us, but at close range, local gravitational interactions dominate. Andromeda and the Milky Way are part of the same gravitational structure, the local group, a collection of about 80 galaxies bound together by gravity. And within that structure, Andromeda is the biggest. It weighs roughly twice as much as the Milky Way, maybe 1 trillion solar masses. And it's coming our way. The collision timeline has been mapped out in detail using data from the Hubble Space Telescope and the Gaia satellite. Hubble measured Andromeda's motion across the sky, tiny shifts in position over the course of years that revealed the galaxy's trajectory. Gaia mapped the positions and velocities of stars in the Milky Way, giving us a precise understanding of our own galaxy's motion. Plug the data into a simulation and you get a prediction. First approach in about 4 billion years, full merger completed in roughly 6 billion years. The first approach will not be the last. The two galaxies will pass through each other, their stars missing each other by vast distances because space is mostly empty. Individual stars almost never collide during a galactic merger. The distances between stars are enormous compared to their sizes. If you scaled the Sun down to the size of a grain of sand, the nearest star would be about 4 miles away. Galaxies are not solid objects. They're clouds of stars, mostly empty space, passing through each other like two handfuls of sand tossed together. But gravity doesn't care about empty space. The gravitational fields of the two galaxies will interact. Tidal forces will pull stars out of their orbits, flinging them into long tails. The disks will warp. Some stars will be ejected from the system entirely, flung out at high speed into intergalactic space. The odds of the Sun being one of those ejected stars is small but non-zero. Current simulations put it at around 10 to 20%. Most likely, the solar system will survive the collision intact, though its orbit around the galactic center will change. We might end up further out. We might end up closer in, but the Sun and its planets, assuming any of them are still around, will hold together. The visual spectacle, if anyone is around to see it, will be extraordinary. Right now, Andromeda looks like a faint smudge. During the approach, it will grow, and grow, and grow. A few 100 million years before the collision, Andromeda will be bright enough to cast shadows at night. Its disk will span more than 100 degrees across the sky, larger than the full moon by a factor of 50. You could hold your arms out at full width and still not cover it. The sky will be dominated by a glowing band of light, brighter than anything except the Sun, stretching from horizon to horizon. And it will stay that way for more than 1 billion years as the two galaxies spiral around each other, passing through, swinging back, passing through again. The final merger will take about 2 billion years from the first approach. By the time it's over, the Milky Way and Andromeda will have merged into a single giant elliptical galaxy. Astronomers have already named it Milkomeda. Some prefer Milkdromeda. Either way, it will weigh somewhere between 3 and 4 trillion solar masses. No disk, no spiral arms, just a smooth, featureless cloud of stars, most of them old and red, with almost no gas left and almost no star formation. A dead galaxy by modern standards, quietly aging, slowly fading. The central black holes will merge too. Sagittarius, a star, the Milky Way's 4 million solar mass black hole, and M31 star, Andromeda's roughly 100 million solar mass black hole, will eventually spiral together and merge into a single black hole weighing about 104 million solar masses. The merger will release a burst of gravitational waves strong enough to be detected by any civilization within a few 100 million light-years, assuming anyone is still around to build detectors. And the resulting black hole will sit at the gravitational center of Milkomeda, holding the stars in orbit, silent and dark, unless something falls into it and lights it up again. This is not speculation. This is not science fiction. This is going to happen. The only uncertainty is the exact timeline. 4 billion years, 5 billion, 6. The numbers shift slightly depending on which simulation you run and what assumptions you make about the initial conditions. But the outcome is the same. Collision, merger, elliptical galaxy, the end of the Milky Way as a distinct object. 4 billion years is a long time. Long enough that the Sun will have already begun its death throes. In about 5 billion years, the Sun will exhaust the hydrogen in its core, expand into a red giant, and swallow the inner planets. Mercury, Venus, possibly Earth. The outer planets might survive, but they'll be baked by the Sun's bloated outer layers. By the time the Andromeda collision is complete, the Sun will be a white dwarf, a dense, cooling ember about the size of Earth, slowly radiating away its remaining heat over trillions of years. If any planets survive, they'll be frozen, lifeless, orbiting a dead star in a galaxy that no longer resembles the one they formed in. But the universe will go on. Milky will be just one of many giant ellipticals scattered across the cosmos, and the mergers won't stop. The local group contains other galaxies. Triangulum M33, the third largest galaxy in the group, will probably merge with Milky eventually. And on larger scales, the Virgo cluster, a massive collection of galaxies about 50 million light-years away, will continue pulling in smaller groups and clusters, growing larger over billions of years. The cosmic web will keep doing what it's been doing for more than 13 billion years, pulling things together, building larger and larger structures, until eventually, trillions of years from now, the accelerating expansion of the universe carries everything beyond the reach of gravity, and the mergers stop. The dance of galactic mergers is not gentle. It's violent, chaotic, and beautiful. Two galaxies, each containing hundreds of billions of stars, each with their own history, their own structure, their own population of planets and moons and clouds of gas, collide and become something new. The stars don't die, the planets don't explode. But the galaxies themselves, the organized structures they belong to, cease to exist. And what emerges is a composite, a hybrid, a galaxy that remembers nothing about where its pieces came from. The evidence of past mergers is everywhere. Every elliptical galaxy is a merger remnant. Every stellar stream is the corpse of a dwarf galaxy. Every tidally disrupted system, every starburst galaxy, every active galactic nucleus lit up by gas funneled inward during a collision, all of it points to the same conclusion. Galaxies are not static. They are not isolated. They are constantly interacting, colliding, merging, and rebuilding themselves from the wreckage. And the process is driven entirely by gravity. The same force that holds you to the surface of the Earth, that keeps the Moon in orbit, that pulls apples toward the ground, is the force shaping the largest structures in the universe. Gravity doesn't care about scale. It works the same way whether you're talking about a kilogram of mass or a trillion solar masses. Pull things together. The closer they get, the stronger the pull, and eventually they merge. But gravity is not the only force at play. There's something else. Something we can't see, something that doesn't emit light, doesn't interact with ordinary matter except through gravity, and yet makes up the vast majority of the mass in every galaxy, every cluster, every structure in the universe. Without it, galaxies wouldn't hold together. Without it, the cosmic web wouldn't exist. Without it, none of this works. We call it dark matter, and it's been hiding in plain sight since the beginning. The ghostly presence, dark matter's dominance, but gravity is not the only force at play. There's something else, something we can't see, something that doesn't emit light, doesn't interact with ordinary matter except through gravity, and yet makes up the vast majority of the mass in every galaxy, every cluster, every structure in the universe. Without it, galaxies wouldn't hold together. Without it, the cosmic web wouldn't exist. Without it, none of this works. We call it dark matter, and it's been hiding in plain sight since the beginning. Here's the problem. When you measure how fast stars orbit around the center of a galaxy, the numbers don't add up. Stars near the edge of a galaxy, the ones sitting tens of thousands of light-years from the core, are moving way too fast. According to the laws of gravity, the ones worked out by Newton in the 1600s and refined by Einstein in the 1910s, stars that far out should be moving slowly. The further from the center you go, the weaker the gravitational pull and the slower the orbit. That's how it works in the solar system. Mercury zips around the Sun in 88 days. Neptune takes 165 years. The outer planets move slower because they're farther from the Sun's gravity well. Galaxies don't behave that way. In the 1970s, an astronomer named Vera Rubin was measuring the rotation speeds of stars in spiral galaxies, expecting to see the same drop-off. She didn't. The stars at the edge of the galaxies were moving just as fast as the ones closer in some cases faster. The rotation curve, a graph plotting orbital speed versus distance from the center, stayed flat all the way out to the edge of the visible disk. It should have been dropping. It wasn't. Rubin wasn't the first to notice this. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies about 300 million light-years from Earth. He measured how fast the galaxies in the cluster were moving relative to each other and calculated how much mass the cluster needed to hold itself together gravitationally. The answer was ridiculous. The visible mass, all the stars and gas he could detect, added up to only about 15% of what the gravitational measurements said had to be there. Zwicky called the missing mass Dunkel Materie, dark matter, matter you couldn't see but that had to be there because otherwise the galaxies in the cluster would have flown apart billions of years ago. Nobody took him seriously. For decades, Zwicky's results sat in the literature as a curiosity, an anomaly. Maybe he'd made a mistake. Maybe the galaxies in the cluster weren't gravitationally bound at all and were just passing through. Maybe the math was wrong. Then Rubin started publishing her rotation curves. Galaxy after galaxy, the same pattern. Flat rotation curves extending far beyond the visible edge of the disk. Stars moving too fast. Way too fast. And this time, the measurements were solid. The data was clean. There was no mistake. The conclusion was unavoidable. Either the law of gravity breaks down at galactic scales, which would require rewriting all of physics, or there's a lot of mass in galaxies that we can't see. Mass that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. But it's there, pulling on the stars, holding the galaxies together. Rubin spent the rest of her career refining the measurements. By the time she died in 2016, she had mapped the rotation curves of more than 200 galaxies. Every single one showed the same thing. Flat curves, too much gravity, dark matter. She never won the Nobel Prize for it, which is one of the more glaring oversights in the history of modern science. But her work is the foundation of everything we now understand about how galaxies are actually structured. The visible part of a galaxy, the stars and gas that emit light, is not the main event, it's the decoration. The lights hung on a much larger invisible framework. That framework is called a dark matter halo, and it's enormous. The Milky Way's dark matter halo extends out to roughly 1 to 2 million light-years from the galactic center. For comparison, the visible disk, the part you see as the Milky Way stretched across the night sky, is only about 100,000 light-years across. The halo is 10 to 20 times wider, and it contains somewhere between 1 and 1.5 trillion solar masses. The visible part of the Milky Way, all 200 billion stars, weighs in at maybe 200 billion solar masses. The halo outweighs the stars by a factor of 5 to 7, maybe more. This is true for every large galaxy. The stars are the minority. Dark matter dominates, and the halos aren't smooth, they have structure. In 1996, a team of astrophysicists named Julio Navarro, Carlos Frenk and Seaman White published a model describing the density profile of dark matter halos. The NFW profile, named after their initials, predicts that dark matter is most dense near the center of the halo and gets less dense as you move outward, not linearly. The density drops off as 1 over the radius near the center and 1 over the radius cubed farther out. The result is a cuspy profile, a sharp peak at the center, a gradual decline in the middle, and a long tail extending out to enormous distances. This profile has been confirmed observationally in dozens of galaxies through gravitational lensing, a technique where astronomers measure how much a galaxy's gravity bends the light from objects behind it. The more mass, the more bending. The shape of the bending tells you how the mass is distributed. And the answer, over and over, is that galaxies sit inside dark matter halos that follow the NFW profile almost exactly. The halos are real, they're not a fudge factor, they're measurable structures with predictable properties. And they were there first, before the stars, before the galaxies. In the early universe, just a few tens of millions of years after the Big Bang, dark matter started clumping together under its own gravity. Ordinary matter, the hydrogen and helium left over from the Big Bang, was still too hot and too energetic to collapse efficiently. Radiation pressure kept pushing it around, but dark matter doesn't feel radiation pressure. It doesn't interact with photons at all. It just pulls. And because it was immune to the forces slowing down ordinary matter, it collapsed faster. Within a few 100 million years, dark matter had formed vast gravitational wells scattered throughout the universe. Halos, invisible scaffolds where gravity was strong enough to start pulling in the hydrogen and helium gas drifting through space. Once the gas fell into those halos and cooled enough, it collapsed further. Stars ignited, galaxies formed, the visible universe lit up. But the foundation, the structure holding it all together, was dark matter. Michael Turner, a cosmologist at the University of Chicago, put it plainly in a 2020 interview. Dark matter is the scaffolding upon which the luminous universe is built. Without it, there are no galaxies. Without it, there are no stars. Without it, there is no structure. Just a thin, cooling fog of hydrogen drifting through an expanding universe, never collapsing into anything interesting. The cosmic microwave background, the afterglow of the Big Bang, provides independent confirmation. The fluctuations in the CMB, the tiny temperature differences measured by satellites like WMAP and Planck, can only be explained if dark matter was already clumping together when the universe was 380,000 years old. The data from Planck, released between 2013 and 2020, pinned down the density of dark matter in the universe to extraordinary precision. Dark matter makes up about 26% of the total energy density of the universe. Ordinary matter, the stuff made of protons and neutrons and electrons, accounts for only about 5%. The rest, roughly 69%, is dark energy, the mysterious force driving the accelerating expansion of the universe. But dark energy is smooth, it's spread evenly throughout space. Dark matter clumps. It has structure, and it's that structure, those halos, that allowed galaxies to form in the first place. Now, here's where things get weird. Because even though dark matter solves the missing mass problem in galaxies, it doesn't solve the missing baryon problem. Baryons are the particles that make up ordinary matter, protons and neutrons, the stuff you're made of. The cosmic microwave background tells us that baryons should make up about 5% of the universe's total energy density. But when astronomers add up all the baryons they can detect, all the stars, all the gas in galaxies, all the clouds of hydrogen drifting between galaxies, they only account for about half of that. The rest of the baryons are missing. They're not missing in the sense that they don't exist. They're missing in the sense that we can't see them easily. It turns out that most of the ordinary matter in the universe isn't in galaxies at all. It's in the space between galaxies, floating in a diffuse warm-hot plasma called the warm-hot intergalactic medium, WIM for short. The temperature of this gas sits somewhere between 100,000 and 10 million degrees Kelvin. Hot enough that it doesn't emit visible light, but not hot enough to glow brightly in X-rays. It's invisible in most wavelengths. You have to look for it using X-ray absorption lines, signatures where the gas absorbs specific wavelengths of light coming from distant quasars. Studies published around 2012 started detecting those absorption lines, confirming that the WIM exists and that it contains most of the missing baryons. So dark matter solves one mystery and creates another. It explains why galaxies hold together. It explains how structure formed in the early universe, but it doesn't explain where all the ordinary matter went. That's a separate problem. The current cosmological model, called lambda CDM, integrates both. CDM stands for cold dark matter, meaning the dark matter particles move slowly relative to the speed of light. Cold dark matter clumps efficiently, forming the halos that seed galaxies. Lambda is the cosmological constant, the term Einstein introduced to describe dark energy. Lambda CDM is the standard model of cosmology, and it works. It explains the cosmic microwave background. It explains the large-scale structure of the universe. It explains galaxy formation, and it predicts the existence of dark matter halos with remarkable precision. But we still don't know what dark matter is made of. We've never directly detected a single particle of it in a laboratory. And it's not for lack of trying. There are dozens of experiments running right now, deep underground, where they're shielded from cosmic rays designed to catch dark matter particles interacting with ordinary matter. The leading candidate is something called a WIMP, weakly interacting massive particle. A hypothetical particle that has mass, feels gravity, but interacts with ordinary matter only through the weak nuclear force, one of the four fundamental forces of nature. If WIMPs exist, they should be passing through the Earth all the time, billions of them every second, streaming through your body, through the walls, through the planet, almost never interacting with anything. But once in a while, very rarely, a WIMP should collide with an atomic nucleus and produce a tiny flash of energy. That's what the detectors are looking for. A flash, a single event, proof. So far, nothing. Experiments like LZ, which started running in 2022, and XEON-T, which came online in 2023, have pushed the sensitivity limits higher and higher. If WIMPs exist and weigh more than 10 giga-electron volts, they should have been detected by now. They haven't been, which means either WIMPs are lighter than expected, or they interact even more weakly than the models predict, or they're not the answer. Another candidate is the axion, a hypothetical particle much lighter than a WIMP, originally proposed in the 1970s to solve a problem in particle physics that has nothing to do with dark matter. It turns out that if axions exist, they could be dark matter. They'd be produced in enormous quantities in the early universe, they'd be stable, and they'd clump gravitationally just like WIMPs. The ADMX experiment, the Axion dark matter experiment, is searching for them. The latest upgrade came online in 2024, scanning a narrow range of masses between 1 and 40 microelectron volts. So far, no detection. As of 2026, we have no direct evidence for what dark matter is made of. None. We know it's there because we can see what it does. We can measure its gravitational effects. We can map its distribution using gravitational lensing. The Euclid telescope, launched by the European Space Agency in 2023, is in the process of mapping dark matter halos across billions of light-years, creating the most detailed three-dimensional map of the cosmic web ever made. And the data is revealing tensions in the lambda CDM model, small discrepancies between what the model predicts and what we observe. The S8 tension, A mismatch between the clumpiness of matter measured from the cosmic microwave background and the clumpiness measured from galaxy surveys is one example. Nobody knows if it's a real problem or just a measurement issue. But it's there. Vera Rubin herself once said, "If dark matter isn't there, we're back to square one." And she was right. Dark matter is the only explanation that fits all the data. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, large-scale structure, all of it points to the same conclusion. There's matter out there, a lot of it, that we can't see. It doesn't emit light. It doesn't absorb light. It doesn't interact with ordinary matter except through gravity. And it holds the universe together. Now, here's where things get stranger. In 2016, a team led by Peter van Dokkum at Yale discovered a galaxy that shouldn't exist. They were using a specialized telescope called Dragonfly, designed to detect extremely faint, diffuse objects that other telescopes miss. And they found something in the Coma cluster, the same cluster Fritz Zwicky studied back in 1933. A galaxy so faint, so spread out, that it was almost invisible. They called it Dragonfly 44. Dragonfly 44 is what astronomers call an ultra-diffuse galaxy, UDG, a galaxy that's about the size of the Milky Way but contains only about 1/100th as many stars. Roughly 100 million solar masses of stars spread out over a region 100,000 light-years across. It should be ripped apart by tidal forces from the surrounding galaxies in the cluster. It should have been destroyed billions of years ago, but it's still there, still intact, still holding itself together. Van Dokkum's team measured the velocity dispersion of stars in Dragonfly 44. Velocity dispersion is a fancy term for how fast stars are moving relative to each other. The faster they move, the more gravity is needed to hold them in orbit. The answer was shocking. The stars in Dragonfly 44 are moving at about 47 kilometers per second. That's way too fast for the amount of visible matter. To hold those stars in orbit, the galaxy needs to weigh about 100 billion solar masses, 1,000 times more mass than the visible stars. Dragonfly 44 is 99.99% dark matter. Van Dokkum called it a ghostly galaxy. A galaxy made almost entirely of dark matter, with just a thin scattering of stars sprinkled throughout like lights on a Christmas tree. The paper was published in Nature, one of the most prestigious journals in science, and it made headlines around the world. Here was direct proof that dark matter could dominate a galaxy to an almost absurd degree. The stars are irrelevant. The dark matter halo is everything. And Dragonfly 44 is not alone. Astronomers have since found dozens of ultra-diffuse galaxies in galaxy clusters, most of them with similarly extreme dark matter fractions. These galaxies are ghosts, faint, diffuse, almost invisible, and yet they contain as much mass as the Milky Way, maybe more, all of it locked up in dark matter halos. The existence of ultra-diffuse galaxies raises a fundamental question. If you can have a galaxy that's 99.99% dark matter, can you have one that's 100%? A dark galaxy, a gravitationally bound cloud of dark matter with no stars at all, just a halo, no light, no gas, nothing. Theoretical models say yes. These objects should exist, and there are hints that we've found them. Clouds of hydrogen detected in radio surveys that seem to have mass but no visible stars. Gravitational lensing signals that suggest the presence of a massive object where no galaxy appears. But confirming their existence is hard because by definition they don't emit much light. If dark galaxies are common, they would add significantly to the galaxy count, and they'd be completely invisible in optical surveys. You'd need radio telescopes, gravitational lensing studies, or extremely sensitive infrared observations to even have a chance of detecting them. Then, in 2018, Van Dokkum's team published another paper. This time, they'd found the opposite. A galaxy called NGC 1052 DF2, another ultra-diffuse galaxy. Same size, same faint appearance. But when they measured the velocity dispersion, the answer was bizarre. The stars were barely moving, less than 10 kilometers per second. The galaxy had almost no dark matter, maybe less than 1%. A galaxy with normal amounts of stars and almost no dark matter halo. This was a problem, because if dark matter halos are the foundation of galaxy formation, how do you end up with a galaxy that has no halo? The paper sparked an immediate controversy. Some astronomers questioned the distance measurement. If NGC 1052 DF2 is closer than Van Dokkum's team thought, the velocity dispersion would need to be recalculated, and the galaxy might have more dark matter than it appears. Others suggested that tidal stripping, the process where a galaxy passing through a dense cluster loses its outer layers to gravitational forces, could have removed the dark matter halo. But tidal stripping usually removes stars too, and NGC 1052 DF2 still has plenty of stars. As of 2026, the debate is ongoing. Some studies have revised the distance upward, suggesting the galaxy has more dark matter than originally thought, maybe 10 to 20%. Others have found additional low dark matter galaxies, suggesting that NGC 1052 DF2 is not a fluke. The picture is messy, and that's the point. Dark matter dominates most galaxies, but not all of them. There are outliers, galaxies with almost no dark matter, galaxies with nothing but dark matter, and we don't fully understand why. One possibility is that ultra-diffuse galaxies are the result of tidal interactions. A normal galaxy falls into a massive cluster, gets pulled and stretched by the gravity of the surrounding galaxies, and loses most of its stars. What's left is a puffed-up halo with a few stars clinging to it. Another possibility is that these galaxies formed differently. Maybe they started out as normal dwarf galaxies but experienced a burst of star formation early in their lives. The supernova explosions from those stars blew out most of the gas, preventing further star formation, and the galaxy ended up with a large dark matter halo and very few stars. Nobody knows for sure. The data is too new. The observations are still being refined. But the existence of ghost galaxies, whether they're dominated by dark matter or almost devoid of it, proves that galaxy formation is not a one-size-fits-all process. There are extremes, outliers, galaxies that break the rules, and every one of them is a clue to how dark matter actually behaves in the real universe, not just in simulations. There's also a theory that challenges the entire dark matter paradigm. It's called MOND, Modified Newtonian Dynamics, proposed by Mordechai Milgram in 1983. MOND suggests that the law of gravity itself changes at very low accelerations, the kind of accelerations you find at the outer edges of galaxies. If gravity gets slightly stronger than Newton predicted when accelerations are weak, you don't need dark matter to explain flat rotation curves. The stars at the edge of the galaxy are moving fast because gravity is pulling harder than we thought. MOND fits galaxy rotation curves remarkably well. Better than dark matter in some cases, but it has problems. Big ones. It can't explain the bullet cluster. It can't explain gravitational lensing. It can't explain the cosmic microwave background. MOND works at galactic scales but breaks down everywhere else. Most physicists have abandoned it, not because it's wrong, but because it doesn't solve enough problems. Dark matter, for all its mysteries, explains more. The search for dark matter is one of the largest coordinated efforts in modern physics. Dozens of experiments, hundreds of scientists, Billions of dollars spent on detectors buried kilometers underground, shielded from cosmic rays, cooled to near absolute zero, waiting for a single dark matter particle to collide with a single atom and give us the answer. So far, nothing. But the absence of a detection doesn't mean dark matter isn't there. It just means it's harder to find than we hoped. Dark matter is the scaffolding, the invisible framework holding galaxies together. Without it, the stars would fly apart. Without it, the cosmic web would collapse. Without it, none of the structures we see today would exist. And yet we can't touch it. We can't see it. We can't even prove what it's made of. We only know it's there because the universe refuses to make sense without it. Every galaxy in the observable universe, every one of those 2 trillion, sits inside a dark matter halo. The halo was there first, forming in the chaotic early universe when the cosmos was just a few 100 million years old. Ordinary matter fell into the halo, collapsed, ignited, and built the galaxy we can see. But the halo remained, invisible, dominant, holding everything in place. The stars are passengers. The dark matter is the ship. And now that we know galaxies can exist with almost no stars, just dark matter, and galaxies can exist with almost no dark matter, just stars, the question becomes, what else is out there? How many galaxies have we missed because they're too faint to see? How many dark halos are floating through space with no stars to mark their location? The 2 trillion galaxy count is just the visible census. The full count, including the ghosts, could be much higher. The universe is not empty, it's full of matter we can't see, full of halos we can't map, full of galaxies that exist at the extremes of what physics allows. And at the center of nearly every one, there's a black hole, a mouth in space. A gravitational singularity that doesn't just sit there passively. It feeds, it regulates, it influences everything around it. And when the galaxy runs out of gas, when the star formation finally stops, when the last generation of massive stars dies in supernova explosions scattering heavy elements into space, the galaxy itself begins its slow march toward the end. Not a dramatic explosion, not a sudden collapse. Just a long, quiet fade. The stars burning out one by one. The gas used up. The black hole going dormant. And what's left is a graveyard, a collection of dead and dying stars, slowly cooling, slowly fading, until the galaxy becomes one more ghost, drifting through the dark. A galaxy's end, stellar demise and cosmic recycling, and now that we know galaxies can exist with almost no stars, just dark matter, and galaxies can exist with almost no dark matter, just stars, the question becomes, what else is out there? How many galaxies have we missed because they're too faint to see? How many dark halos are floating through space with no stars to mark their location? The 2 trillion galaxy count is just the visible census. The full count, including the ghosts, could be much higher. The universe is not empty. It's full of matter we can't see, full of halos we can't map, full of galaxies that exist at the extremes of what physics allows. And at the center of nearly every one, there's a black hole, a mouth in space, a gravitational singularity that doesn't just sit there passively. It feeds, it regulates, it influences everything around it. And when the galaxy runs out of gas, when the star formation finally stops, when the last generation of massive stars dies in supernova explosions, scattering heavy elements into space, the galaxy itself begins its slow march toward the end. Not a dramatic explosion, not a sudden collapse, just a long, quiet fade, the stars burning out one by one, the gas used up, the black hole going dormant, and what's left is a graveyard, a collection of dead and dying stars, slowly cooling, slowly fading, until the galaxy becomes one more ghost drifting through the dark. This is how galaxies die. Not all at once, not in a blaze of glory. They starve, they run out of fuel, they get stripped, they quench. And the process is happening right now, all across the universe, to roughly half of all massive galaxies. The universe's star formation rate peaked about 10 billion years ago. Since then, it's been dropping steadily, inexorably. We're now forming stars at a rate about 100 times lower than the peak, and in another 10 to 100 billion years, star formation will effectively cease. The universe will go dark, not because the stars will explode or disappear, but because no new ones will be born. Let's start with what astronomers call quenching. The word makes it sound gentle, like you're turning off a burner on a stove. In reality, it's the process by which a galaxy stops forming stars, and it's one of the most violent, disruptive, and poorly understood transitions in all of astrophysics. A galaxy spends billions of years forming stars, building structure, growing larger, and then suddenly, or sometimes gradually, it stops. The gas runs out, the fuel disappears, and the galaxy transitions from blue, actively star-forming, to red and dead. An elliptical or a lenticular, smooth, featureless, full of old stars that will never be replaced. The question is, why? What stops the star formation? And the answer depends on where the galaxy is and what's happening to it. There are two broad categories of quenching: internal and environmental. Internal quenching happens when something inside the galaxy shuts down star formation. Environmental quenching happens when the galaxy's surroundings do the job. Both are common, both are efficient, and both lead to the same endpoint: a red, quiescent galaxy with no gas left and no future. Let's start with the internal mechanisms, because they're the ones most galaxies experience regardless of where they live. The simplest is gas depletion. A galaxy forms stars by collapsing clouds of hydrogen and helium gas. Stars are made of gas. Planets are made of gas that condensed into solids. Everything in a galaxy that isn't dark matter started as gas, and there's only so much of it. A typical spiral galaxy like the Milky Way contains somewhere between 10 and 50 billion solar masses of gas. Most of it is sitting in the disk, in giant molecular clouds scattered throughout the spiral arms. Every year, the Milky Way forms about 1 to 2 new solar masses worth of stars. At that rate, we'll run out of gas in a few billion years, maybe 10 billion, maybe 20. The exact number depends on how efficiently we convert gas into stars and how much new gas we can pull in from the surroundings. But the point is, the clock is ticking. Eventually the gas runs out, and when it does, star formation stops. Not immediately, the process is gradual. Fewer and fewer molecular clouds, fewer and fewer star-forming regions. The spiral arms fade. The disk grows dim, and what's left is a galaxy full of aging stars, slowly burning through the last of their fuel. But galaxies don't just passively consume their gas, they can lose it. Supernovae are the main culprit. When a massive star dies, it explodes with enough energy to blow gas out of the surrounding region at thousands of kilometers per second. One supernova can clear out a bubble of space several hundred light-years across. And when you have thousands or millions of supernovae happening over the lifetime of a galaxy, all that gas being blown outward, a significant fraction of it escapes the galaxy entirely. This is called supernova-driven outflows, and it's one of the primary ways galaxies lose their star-forming fuel. The effect is strongest in small galaxies. Dwarf galaxies, the ones weighing in at only a few million or a few billion solar masses, have weak gravitational fields. It doesn't take much energy to blow gas out of them completely. One burst of star formation, a few dozen massive stars forming at once, dying within a few million years, and the resulting supernovae can expel most of the remaining gas. The galaxy quenches, star formation stops, and what's left is a small, faint gas-poor system full of old stars. The local group, the collection of about 80 galaxies surrounding the Milky Way and Andromeda, is full of these quenched dwarfs. Most of them stopped forming stars billions of years ago. They've been coasting ever since, slowly fading. Larger galaxies are harder to quench this way because they have deeper gravity wells. It takes more energy to blow gas out of a galaxy the size of the Milky Way. Supernovae help, but they're not enough on their own. Which brings us to the second internal mechanism, active galactic nuclei, black holes. We've already talked about how supermassive black holes feed and release energy. When a black hole at the center of a galaxy is actively accreting, feeding on gas from the surrounding disk, it doesn't just swallow everything that falls in. A significant fraction of the energy released by the infalling material gets radiated outward or flung away in powerful jets and winds. That energy slams into the surrounding gas, heating it, ionizing it, and in many cases pushing it outward so hard that it escapes the galaxy entirely. This is AGN feedback, and it's one of the most efficient quenching mechanisms in the universe. The numbers are staggering. A supermassive black hole feeding at the Eddington limit, the maximum rate at which it can accrete without blowing away its own fuel, releases about 10% of the infalling mass as energy. That's E equals mc squared in action. A small amount of mass converted into a huge amount of energy. And when that energy couples to the gas in the galaxy, heating it to temperatures of millions of degrees, the gas can no longer cool down and collapse to form stars. It's too hot. It expands. It gets blown out, and the galaxy quenches. This process is most effective in the most massive galaxies. Giant ellipticals sitting at the centers of galaxy clusters, weighing in at trillions of solar masses, have enormous central black holes, billions of solar masses. When those black holes turn on, they can pump enough energy into the galaxy to unbind most of the remaining gas. The Silk and Rees model, published in 1998, predicted exactly this. The black hole grows until its feedback energy becomes strong enough to expel the gas from the galaxy. At that point, the galaxy stops growing, the black hole stops growing, and the system reaches a quenched state. Observations from the James Webb Space Telescope, published between 2023 and 2024, have confirmed this in the early universe. Webb has found massive quenched galaxies at redshifts greater than 6, less than 1 billion years after the Big Bang. Galaxies that should still be forming stars are already red and dead, and the only mechanism that can quench a galaxy that fast is AGN feedback. The central black hole turned on, fed aggressively for a few tens of millions of years, blew out the gas, and shut down star formation before the galaxy even had time to finish assembling. The correlation between black hole mass and galaxy quenching is tight. Priyamvada Natarajan at Yale has shown that the most massive galaxies, the ones with the largest central black holes, are also the ones most likely to be quenched. The black hole doesn't just regulate star formation. In many cases, it ends it permanently, and the galaxy transitions from a blue star-forming system to a red quiescent one in less than 1 billion years, sometimes much faster. Now let's talk about environmental quenching, because if you live in a galaxy cluster, you're not going to make it. Galaxy clusters are the most massive gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies packed into a region a few million light-years across. The Virgo cluster, the nearest large cluster to us, sits about 50 million light-years away, and contains more than 2,000 galaxies. The Coma cluster, the one Fritz Zwicky studied back in the 1930s, contains more than 1,000, and the space between those galaxies is not empty. It's filled with hot gas. The intracluster medium, a diffuse plasma heated to tens of millions of degrees by the gravitational energy of the cluster itself. When a gas-rich spiral galaxy falls into a cluster, it's doomed. The galaxy is moving fast, hundreds or thousands of kilometers per second, and as it plows through the intracluster medium, the hot gas outside the galaxy pushes against the cold gas inside. This is called ram pressure, the same force you feel when you stick your hand out the window of a moving car. The faster you move, the harder the wind pushes. For a galaxy moving through the intracluster medium, the ram pressure is strong enough to strip the gas right out of the disk, literally rip it away and leave it trailing behind in a long tail. The process is called ram pressure stripping, and it's brutal. A spiral galaxy entering a cluster can lose 90 to 100% of its gas in just 100 to 500 million years. That's fast. Galactic timescales are measured in billions of years. Losing all your gas in 500 million years is like losing all the water in a lake over a single summer. The galaxy doesn't have time to adjust. Star formation drops off a cliff. The spiral arms fade. The disk dims. And within 1 billion years, the galaxy has transformed into a lenticular or an elliptical. Red, smooth, dead. The Virgo cluster is full of these galaxies. Astronomers have been mapping them for decades, and the pattern is clear. The closer a galaxy is to the center of the cluster, the more likely it is to be quenched. Galaxies on the outskirts, the ones that just entered the cluster, still have gas, still forming stars. Galaxies near the center, the ones that have been in the cluster for billions of years, are almost all red and dead. No gas, no star formation, just old stars slowly aging. The Hubble Space Telescope captured stunning images of ram pressure stripping in action. One galaxy, NGC 4330, a spiral falling into the Virgo cluster, is leaving a tail of gas stretching behind it for more than 200,000 light-years. The tail is glowing with newborn stars, regions where the stripped gas compressed and ignited as it was torn away. But the galaxy itself, the main body, is running out of fuel. In another few 100 million years, the tail will disperse. The stars in it will fade, and NGC 4330 will be just another red elliptical in the cluster, indistinguishable from the hundreds of others that met the same fate. There's another environmental mechanism that's even more violent: tidal interactions. When a small galaxy passes close to a larger one, the difference in gravitational pull between the near side and the far side of the smaller galaxy can be strong enough to tear it apart. This is the same tidal force that creates ocean tides on Earth, but on a galactic scale. The smaller galaxy gets stretched. Stars and gas get pulled out into long streams. Some of the material falls into the larger galaxy and merges with it. Some gets flung out into intergalactic space and lost forever. The Milky Way is doing this right now to the Sagittarius dwarf elliptical galaxy. The Sagittarius stream, the long ribbon of stars wrapping around the Milky Way, is the debris, the dwarf galaxy itself. What's left of it is still there, but it's been shredded. In a few billion years, it will be gone completely, dissolved, its stars absorbed into the Milky Way's halo. And the Milky Way will be slightly more massive, slightly richer in stars. And nobody looking at the sky will know there was ever a separate galaxy there. Tidal stripping can also remove gas from galaxies without destroying them completely. A small galaxy passing near a larger one can lose its outer layers, the gas and stars farthest from the center, while the core remains intact. What's left is a compact, gas-poor galaxy that can no longer form stars, quenched by tidal forces rather than by ram pressure or AGN feedback. The result is the same: a red, dead galaxy, no future. About half of all massive galaxies in the universe today are quenched, red and dead. No star formation, no gas, just old stars slowly fading. The fraction is even higher in galaxy clusters where environmental quenching is common. In the densest clusters, more than 90% of the galaxies are red. The intra-cluster medium has stripped the gas from nearly every spiral that ever fell in. The only galaxies still forming stars in those environments are the ones that just arrived, the newcomers, and they won't last long. This raises a question. If half the galaxies in the universe are already dead, what does that mean for the future? The answer is uncomfortable. The universe's star formation rate peaked about 10 billion years ago, when the cosmos was roughly 3 to 4 billion years old. At that time, galaxies were forming stars at a rate about 100 times higher than they are today. The early universe was a factory, gas was abundant, galaxies were colliding and merging constantly. Every collision triggered a starburst, and the universe was lighting up. Since then, the rate has been dropping steadily. The gas is being used up. Galaxies are quenching. Mergers are less frequent because the universe is expanding and galaxies are drifting apart. The fuel is running out. And in another 10 to 100 billion years, star formation will effectively cease. Not completely. There will still be occasional bursts when two gas-rich galaxies happen to collide, but those events will become rarer and rarer as the universe ages. Eventually, the last stars will form. The last molecular clouds will collapse, and the universe will enter a phase where no new stars are being born. What happens then? The stars that already exist will keep burning. For a while, the longest-lived stars, the small red dwarfs, can burn for trillions of years, but even they will eventually run out of fuel. When they do, they'll cool off and become brown dwarfs, failed stars. Dim, faint, radiating only in the infrared. The universe will be full of them. Trillions upon trillions of cooling embers drifting through space. The more massive stars, the ones like the Sun, will die much sooner. In about 5 billion years, the Sun will exhaust the hydrogen in its core, expand into a red giant, and eventually shed its outer layers, leaving behind a white dwarf, a dense, cooling core about the size of Earth, slowly radiating away its remaining heat over trillions of years. Most of the stars in the universe will meet the same fate. They'll burn through their fuel, swell up, blow off their outer layers, and leave behind white dwarfs, and the galaxies they belong to will become graveyards. Collections of white dwarfs, brown dwarfs, and black holes, slowly cooling, slowly fading. This isn't speculation. This is the standard model of stellar evolution, confirmed by decades of observations. We know how stars die because we've watched them do it. We've seen planetary nebulae, the glowing shells of gas blown off by dying stars. We've seen white dwarfs, the remnants left behind. We've mapped their cooling curves, the rate at which they lose heat over time, and we've run the simulations forward. In 10 to the 14th years, 100 trillion years, every star in the universe will have burned out. The last red dwarf will fade. The last white dwarf will cool to the point where it no longer emits visible light, and the universe will be dark. But the story doesn't end there, because even though the galaxies are quenching, even though star formation is dropping, the universe is not just throwing the gas away, it's recycling it. Every star that dies, every supernova that explodes, every planetary nebula that puffs off its outer layers, all of that material gets scattered back into space, and it doesn't just vanish, it drifts, it cools, and eventually it can collapse again. This is cosmic recycling. The heavy elements forged in the cores of massive stars, carbon, oxygen, nitrogen, iron, are ejected into the interstellar medium when the stars die. That enriched gas mixes with the primordial hydrogen and helium left over from the Big Bang. And when the next generation of stars forms, they're made of that mix. More metals, more heavy elements. Each generation of stars is slightly richer in heavy elements than the last, because each generation inherits the debris of the ones that came before. The Sun is a third-generation star, maybe fourth. We know this because the Sun contains about 2% heavy elements by mass, metals in astronomers' terms, everything heavier than helium. Those metals didn't exist in the early universe. They were forged in stars that lived and died billions of years before the Sun formed. When those stars exploded, they seeded the molecular cloud that eventually collapsed to form the Sun and the solar system. Every atom of carbon in your body, every atom of oxygen, every atom of iron in your blood was created in a star that died before the Sun was born. You are made of recycled stardust. That's not poetry. That's chemistry. This recycling process has been running for more than 13 billion years, and it will keep running as long as there's gas left to collapse. But the gas is running out. The universe has used up most of it. The star formation rate has dropped by a factor of 100 from its peak, and it's still dropping. The fuel is finite, and we're burning through it. In another 10 to 100 billion years, the recycling process will slow to a crawl. Not because the stars stop dying, they'll keep dying, but because the gas they eject won't have anywhere to go. It won't collapse into new stars because the universe will have expanded so much that the gas clouds will be too diffuse to collapse. Gravity will still pull, but the expansion of space will pull harder, and the gas will just drift forever. The concept of red and dead galaxies is not a metaphor. It's a literal description of what happens when a galaxy finishes its life cycle. The red comes from the color of the stars. When a galaxy stops forming stars, the blue, massive, short-lived stars die off within a few million years. What's left are the red, low-mass, long-lived stars, red dwarfs, red giants, old stars. Stars that have been burning for billions of years and will keep burning for billions more. But they're dim. They don't produce much light, and they give the galaxy a reddish hue. The dead part is self-explanatory. No new stars, no star formation, no future. Red and dead galaxies are everywhere. They dominate the centers of galaxy clusters. They make up about 50% of all massive galaxies in the universe today, and their prevalence tells us something fundamental about galaxy evolution. Galaxies don't live forever. They have a life cycle: birth, growth, maturity, decline, death. Just like stars, just like planets, just like everything else in the universe, the difference is scale. A star lives for millions or billions of years. A galaxy can live for tens of billions of years, but eventually it runs out of fuel, it quenches, it transitions from blue to red, and it joins the graveyard. The universe is filling up with these dead galaxies, and the process is accelerating. The expansion of the universe is accelerating, driven by dark energy, the mysterious force that makes up about 69% of the universe's total energy density. As the expansion accelerates, galaxies drift farther apart, collisions become rarer, gas inflows stop, and more galaxies quench. By the time the universe is 100 billion years old, the star formation rate will be less than 1% of what it is today. By 1 trillion years, it will be effectively zero. And by 10 to the 14th years, 100 trillion years, every star in the universe will have burned out. The galaxies will be dark. The clusters will be dark. The universe itself will be dark, not because the matter disappeared, but because it stopped shining. There's a term for this, the heat death of the universe. It's the endpoint of the second law of thermodynamics, the law that says entropy always increases, energy spreads out, hot things cool down, order decays into disorder, and eventually the universe reaches a state of maximum entropy where no more work can be done, no more energy can be extracted. Everything is the same temperature, everything is at equilibrium, and nothing ever changes again. That's where we're headed. Not tomorrow, not in 1 billion years, but eventually. The universe has an expiration date, and when it arrives, the galaxies we've been talking about, the 2 trillion systems full of stars and gas and black holes and dark matter, will all be gone, not destroyed, not collapsed, just faded, cooled, dead, drifting through an expanding, darkening void that will never light up again. But we're not there yet. Right now, the universe is still active. Stars are still forming. Galaxies are still colliding. Black holes are still feeding. And in the space between the quenched galaxies and the dead ones, there are still billions of systems actively building stars, actively evolving, actively doing what galaxies have been doing for more than 13 billion years, growing, changing, living. And every one of those galaxies, every one of those 2 trillion, is a time capsule, a record of cosmic history frozen in light. The galaxies we see at the edge of the observable universe, the ones whose light has been traveling toward us for more than 13 billion years, are not just distant, they're ancient. We're seeing them as they existed when the universe was less than 1 billion years old. And the galaxies closer to us, the ones whose light took only a few million or a few billion years to reach us, are snapshots from different eras, different moments in cosmic time. When we look at the sky, we're not seeing the universe as it is, we're seeing the universe as it was. Every galaxy is a glimpse into the past, and by studying them, by mapping their distances, their compositions, their star formation rates, their black hole masses, we can piece together the entire history of the cosmos, from the moment the first stars ignited to the slow fade happening now, from the chaotic starburst-filled early universe to the red, quenched, dying galaxies dominating the modern era. Every galaxy tells a story, and if we know how to read them, those stories reveal everything. Where we came from, what we're made of, and where we're going. Galaxies as time capsules, looking back, peering forward, we need to talk about something unsettling. Every galaxy you've ever seen in a photograph, every spiral arm, every glowing core, every smudge of light labeled with a catalog number and a redshift value is a lie. Not in the sense that the image is fake or the data is wrong, but in the sense that what you're looking at doesn't exist anymore, not in the form you're seeing it. The galaxy you're observing, the one captured by the Hubble Space Telescope or the James Webb Space Telescope or some ground-based observatory in Chile, that galaxy is gone. It's not there, not as you see it, because the light you're looking at is old, very old, in some cases older than the Earth, older than the Sun, older than anything you've ever touched or known. The photons reaching the telescope tonight left that galaxy billions of years ago, and they've been traveling through expanding space ever since, carrying a message from a moment in cosmic history that no longer exists. This is the fundamental strangeness of astronomy. You are not looking at the universe as it is. You are looking at the universe as it was. And the further you look, the further back in time you see. Light has a speed limit, 300,000 kilometers per second. Nothing in the universe can travel faster. That's not a technological limitation, that's a law. The speed of light in a vacuum is fixed, and it has been that speed since the beginning of time. which means that light from distant objects takes time to reach us, a lot of time. Light from the sun takes about 8 minutes to reach Earth. If the sun exploded right now, you wouldn't know it for 8 minutes because the light from the explosion, the only way the information could reach you, would still be on its way. You'd sit there in daylight, completely unaware that the sun had just ceased to exist, until the moment the wavefront of darkness swept across the planet and the sky went black. Scale that up. The nearest star to the sun, Proxima Centauri, is about 4.2 light-years away. The light you see from it tonight left that star 4.2 years ago. If Proxima Centauri exploded tomorrow, we wouldn't know until the year 2031. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light-years away. The light reaching us tonight left Andromeda 2.5 million years ago, when Homo habilis was just beginning to use stone tools on the plains of Africa. You are not seeing Andromeda as it is now. You are seeing it as it was before humans existed in any form you'd recognize, and the galaxies sitting at the edge of the observable universe, the ones detected by Webb at redshifts of 14 or higher, their light has been traveling toward Earth for more than 13 billion years. The universe itself was only a few 100 million years old when that light began its journey. The galaxies you're seeing in those images are infants, proto-galaxies, the first generation, and by now, today, at this moment, those galaxies have had more than 13 billion years to evolve, merge, grow, and become something completely different. You will never see what they look like now. You can't. The light showing you their current state won't reach Earth for another 13 billion years. And by that time, assuming anyone is still around to look, the solar system will be long gone. This is what astronomers mean when they say that telescopes are time machines, not in the science fiction sense, in the literal sense. When you point a telescope at a distant galaxy, you are looking backward through time. The further the galaxy, the older the light, and the further back in history you see. The observable universe is not a snapshot of a single moment, it's a timeline, a stitched-together collage of images from every era of cosmic history, all arriving at Earth simultaneously, because the light from each era has been traveling for a different amount of time. The galaxies 10 billion light-years away are showing you what the universe looked like 10 billion years ago. The galaxies 1 billion light-years away are showing you what it looked like 1 billion years ago. And the galaxies in our local neighborhood, the ones only a few million light-years away, are showing you the recent past. Relatively speaking, 2 million years ago is recent on cosmic timescales, even though it predates modern humans by more than 1 million years. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, is the oldest light in the universe. It was emitted when the universe was 380,000 years old, the moment the fog cleared and photons could finally travel freely through space. That light has been traveling toward us for 13.8 billion years, stretched by the expansion of the universe from visible wavelengths all the way into microwaves. When the Planck satellite mapped the cosmic microwave background between 2009 and 2013, it wasn't just mapping the distribution of radiation, it was mapping the universe as it existed 380,000 years after the Big Bang, a baby universe. Hot, dense, smooth, with only the tiniest fluctuations in temperature and density that would eventually grow into galaxies, clusters, and the cosmic web. Every measurement, every temperature map, every data point was a window into the distant past, and that window is closing. The light from the cosmic microwave background has already reached us. There's no older light to see. The CMB is the edge, the horizon. Beyond that, the universe was opaque. No light could travel, And so the history before that moment is invisible to us, locked behind a wall of plasma that no telescope can ever penetrate. The James Webb Space Telescope is currently staring at that wall, or as close to it as physics allows. Webb was built to observe the earliest galaxies, the ones forming just a few 100 million years after the Big Bang. And it's finding them. Galaxies at redshifts of 12, 13, 14. Bright, massive, fully formed systems sitting at distances where the universe was less than 500 million years old. These are the oldest galaxies ever observed, the most distant, the furthest back in time we've ever looked. And they're not what anyone expected. They're too large, too bright, too mature. They shouldn't have had time to assemble yet. The model said they'd be faint smudges, dim proto-galaxies struggling to ignite their first stars. Instead, they're blazing. Some of them rival the Milky Way in mass. Some have central black holes weighing hundreds of millions of solar masses, and they existed less than 500 million years after the universe began. The timeline doesn't fit. The physics struggles to explain it. And the data keeps coming in, image after image, galaxy after galaxy, all of them sitting in the earliest moments of cosmic history, fully formed, as if the universe hit fast forward and nobody told us. This is the power of looking back in time. You don't just see galaxies, you see the history of the universe itself. The early universe was smaller, denser, hotter. The galaxies were closer together. Collisions were more common. Star formation rates were 100 times higher than they are today. The cosmic microwave background shows us the smooth, featureless early universe. Webb shows us the moment it stopped being smooth, the moment structure emerged, the moment the first galaxies lit up and began the long, slow process of turning a cloud of hydrogen and helium into the 2 trillion systems we can count today. Every galaxy Webb detects is a data point, a single frame in a movie that spans more than 13 billion years. And by collecting enough frames, by looking at enough galaxies at different distances, different redshifts, different eras, astronomers can reconstruct the entire story: how galaxies formed, how they grew, how they merged, how they died. The universe is writing its own history, and we're reading it one photon at a time. But there's a problem. The universe is not cooperating, it's expanding. And not just expanding, accelerating. In 1998, 2 independent teams of astronomers, one led by Saul Perlmutter and the other by Adam Rees and Brian Schmidt, were measuring the distances to distant supernovae, trying to figure out whether the universe's expansion was slowing down over time due to the pull of gravity. The expectation was that it had to be slowing. Gravity pulls everything together. The expansion should be decelerating. What they found instead was the opposite. The universe's expansion is speeding up. Galaxies are moving away from us faster now than they were 1 billion years ago, faster than they were 10 billion years ago. The further away a galaxy is, the faster it's receding, and the rate of recession is increasing. This discovery won the Nobel Prize in 2011, and it broke cosmology, because nothing in the standard model predicted it. Gravity pulls, it doesn't push. The only way the expansion can accelerate is if there's something else, some kind of energy permeating all of space, pushing outward, overpowering gravity on the largest scales. Astronomers call it dark energy, and it makes up about 69% of the total energy density of the universe. We have no idea what it is. No theory of physics predicts it. No experiment has ever detected it directly. We only know it's there because the universe is accelerating, and there's no other explanation that fits. Dark energy has consequences, serious ones. The accelerating expansion means that there is a horizon, a boundary beyond which light will never reach us no matter how long we wait. Right now, The observable universe spans about 93 billion light-years from edge to edge. That's the distance light has been able to travel since the Big Bang, accounting for the expansion of space during the journey. But the expansion is accelerating, which means that galaxies beyond a certain distance are receding from us faster than the speed of light. Not because they're moving through space faster than light, which is impossible, but because the space between us and them is expanding faster than light can cross it. Space isn't a thing, it's the distances between things, and there's no speed limit on how fast distances can grow. The result is that there are galaxies out there right now whose light will never reach us. They're outside the observable universe, permanently, and the boundary is getting closer. Galaxies that we can see today will eventually cross that horizon and vanish from view. Not because they stopped existing, but because the universe is pulling them away from us faster than their light can catch up. If you wait long enough, trillions of years into the future, observers in our galaxy will look out and see almost nothing. The local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions will have merged into a single giant elliptical galaxy. Everything else will have been carried beyond the horizon by the expansion of space. Future astronomers will look at the sky and conclude they live in a universe that contains exactly one galaxy, theirs. They will have no way of knowing that there were ever any others. The evidence will have left the building. The cosmic microwave background will have redshifted into undetectability. The distant galaxies will have vanished, and the only objects visible will be the ones gravitationally bound to the local system, the ones close enough that gravity overpowers the expansion. Everything else will be gone, forever. This is already happening in reverse. The 2 trillion galaxies we can see now are only the ones whose light has had time to reach us and whose distance hasn't yet carried them beyond the horizon. There are more galaxies out there, many more. The entire universe, not just the observable slice, could be infinite. And if it is, then the number of galaxies is also infinite. 2 trillion is just the number we can, in principle, observe. It's the size of the fishbowl we're swimming in, not the size of the ocean, and the fishbowl is shrinking, not physically. We're not getting smaller, but the observable universe, the bubble of space from which light can reach us, is approaching a maximum size. In the far future, it will start contracting as galaxies cross the horizon faster than new ones enter the observable region. The universe will still be expanding, but from our perspective, it will look like it's emptying out. The accelerating expansion also means that the universe has an expiration date, not in the sense that it will collapse or explode, but in the sense that it will eventually reach a state where nothing interesting happens anymore. The heat death of the universe, the endpoint of the second law of thermodynamics. Entropy always increases. Energy spreads out, hot things cool down, order decays into disorder, and eventually the universe reaches maximum entropy. Everything is the same temperature, everything is at equilibrium, no more work can be done, no more energy can be extracted. The stars will have burned out, the black holes will have evaporated through Hawking radiation. The galaxies will be dark, lifeless collections of stellar remnants drifting through an expanding void, and nothing will ever change again. That's tens of trillions of years away. Maybe 100 trillion, maybe longer. The exact number depends on the details of dark energy and whether it stays constant or changes over time. But the direction is clear. The universe is headed toward a state where structure disappears, complexity fades, and the cosmic story ends not with a bang, but with a long, slow dimming into nothing. But we're not there yet. Right now, the universe is still writing its story. Stars are still forming, Galaxies are still colliding. Black holes are still feeding. And humanity, standing on a planet orbiting an average star in an average galaxy, is watching. For the first time in the history of the cosmos, matter has organized itself into something complex enough to ask questions about its own origins, to build telescopes, to measure distances, to map the cosmic web, to count the galaxies and wonder where they came from and where they're going. This is not a small thing. The universe spent 13.8 billion years building stars, assembling galaxies, forging heavy elements, creating planets, and evolving life. And now, in this brief window of cosmic time, one species on one planet has figured out how to look backward through time and see the universe's entire history laid out in the light of distant galaxies. Carl Sagan famously said that we are a way for the cosmos to know itself. That's not just poetry, it's physics. The atoms in your body were forged in stars that died billions of years ago. The carbon, the oxygen, the nitrogen, the iron, all of it was created in stellar cores and scattered into space by supernovae. Those atoms drifted through the interstellar medium, mixed with clouds of hydrogen and helium, and eventually collapsed to form the Sun and the solar system. The Earth formed from the debris. Life emerged. Evolution did its work over billions of years. And now you're sitting here, made of stardust, reading about galaxies. The universe is literally looking at itself through your eyes. Every observation, every measurement, every photograph taken by Hubble or Webb or any telescope ever built is the universe studying its own structure, its own history, its own future, and there's still so much we don't know. The James Webb Space Telescope is the most powerful observatory ever launched, and it's only been operating for a few years. The images it's sending back are already rewriting the textbooks. But Webb has limitations. Its mirror is 6.5 meters across, large by space telescope standards, but tiny compared to what's coming next. The next generation of ground-based telescopes, the extremely large telescope in Chile with its 39-meter mirror, the 30-meter telescope if it ever gets built, the giant Magellan telescope with its collection of 7 smaller mirrors arranged into a single effective aperture, these instruments will have the light-gathering power to detect galaxies that Webb can't reach, fainter objects, more distant systems. Galaxies at the very edge of the observable universe, sitting at redshifts of 20 or higher, seen as they existed just 100 million years after the Big Bang, the first generation, the galaxies that formed before anything else. If those galaxies exist, and the models say they should, the next generation of telescopes will find them. And then there's the question of what we're not seeing. The 90% of galaxies that are too faint, too distant, or too obscured to show up in current surveys. The dark galaxies, the ultra-diffuse systems, the dwarf galaxies scattered throughout the voids, all of them contributing to the total count but invisible to us because we haven't looked hard enough or in the right wavelengths. The 2 trillion galaxy census is a lower bound. The true number could be 5 trillion, 10 trillion. We won't know until we build better instruments and spend decades mapping the sky in every wavelength from radio to gamma rays, and even then we'll only see a fraction. The galaxies beyond the horizon, the ones receding faster than light, are lost to us forever. They exist, they're out there, but we will never observe them. The universe is larger than the observable universe, possibly infinitely larger, and most of it is hidden behind a boundary we can never cross. This raises a philosophical question that's been bothering astronomers and physicists for decades. If we can never observe most of the universe, if the expansion is hiding more and more of it from us every second, does it even matter that it exists? Is the observable universe the only universe that matters? Or is there something profoundly unsatisfying about the idea that the cosmos extends infinitely in all directions, full of galaxies and stars and planets and possibly life, and we're trapped in a bubble, watching the rest of it disappear beyond the horizon, knowing it's there but unable to ever reach it or see it or learn anything about it? There's no answer to that question, not a scientific one. It's a matter of perspective. Some scientists find it humbling. The universe is so much larger than us, so much older, so much more complex, that even our most powerful instruments can only glimpse a tiny fraction of it. Others find it frustrating. We've come so far. We've mapped the cosmic web, counted the galaxies, traced the history of star formation back to the earliest moments after the Big Bang, and now we're being told that most of the universe is off-limits forever. But there's a third perspective, and it's the one that keeps astronomers building telescopes, writing proposals, analyzing data, and staring at the sky night after night. The perspective that says we don't need to see everything to understand the rules. The observable universe is a representative sample. The galaxies we can see, the 2 trillion systems spanning 93 billion light-years, are governed by the same physics that governs the galaxies beyond the horizon. Gravity works the same way everywhere. Stars form the same way. Black holes grow the same way. Dark matter clumps the same way. The cosmic web extends infinitely in all directions, but the structure we see here, in our corner of the cosmos, is a fair representation of what's happening everywhere else. We don't need to visit every galaxy to understand how galaxies work. We just need to study the ones we can reach. And we've been doing that for 100 years, and we've learned an astonishing amount. A century ago, we thought the Milky Way was the entire universe. Edwin Hubble changed that in 1923 when he measured the distance to Andromeda and proved it was a separate galaxy, far beyond the Milky Way's edge. In 1929, Hubble discovered that the universe is expanding, that galaxies are moving away from us, and that the further they are, the faster they recede. In 1963, astronomers discovered quasars, realizing that supermassive black holes sit at the centers of galaxies and regulate their evolution. In 1998, they discovered that the expansion is accelerating, driven by dark energy. In 2016, they revised the galaxy count from 100 billion to 2 trillion. And in 2023, the James Webb Space Telescope started finding massive galaxies at redshifts that shouldn't be possible, forcing a re-examination of the entire timeline of galaxy formation. Every decade brings new discoveries, new puzzles, new questions, and that's the point. The universe is not a static object we're cataloging. It's a dynamic, evolving system that's still revealing itself. The story of the cosmos is not finished. We're living in the middle of it. The universe has been expanding and cooling for 13.8 billion years. Star formation peaked 10 billion years ago and has been dropping ever since. In another 10 to 100 billion years, star formation will effectively cease. The last stars will form, the last galaxies will merge, and the universe will enter a long, slow fade into darkness. But that hasn't happened yet. Right now, stars are still lighting up, galaxies are still colliding, black holes are still feeding, the cosmic web is still evolving, and humanity is here, watching, measuring, trying to understand it all before the lights go out. Here we are, standing on a rock orbiting an ordinary star in an ordinary galaxy, one of 2 trillion, staring out at a universe so large that 90% of it is invisible, and most of what remains will vanish beyond the horizon before we ever get close. Every photon that reaches our telescopes is a message from the past. Every galaxy we see is already gone, transformed by billions of years we'll never witness. The light crossing space right now carries news from eras when the Earth didn't exist, when the Sun was still a collapsing cloud, when the Milky Way was a fraction of its current size and the universe itself was young enough that the rules we thought we understood hadn't finished writing themselves yet. 2 trillion galaxies, each one a city of hundreds of billions of stars. Each star potentially surrounded by planets, each planet a world with its own geology, its own chemistry, its own chance, however remote, of hosting something that looks up and wonders what else is out there. The numbers stop meaning anything after a while. Your brain wasn't built to hold that much scale, but the implications don't go away just because they're uncomfortable. Somewhere in that 2 trillion, right now, at this exact moment, there are galaxies forming stars. Galaxies colliding, galaxies dying, black holes feeding, supernovae scattering heavy elements into space, planets cooling, moons forming, and all of it happening without us, without witnesses, without anyone to measure it or name it or care that it's happening at all. Except we do care. For reasons we still don't fully understand, the universe built something capable of looking back at itself and asking why. And that might be the strangest thing of all. Not the 2 trillion galaxies,